Hello, everybody. I know you're probably not expecting to see this face, but if you may remember me from the previous episodes, my name is Michael Francis, and today we have a surprise AskTanmay special. Now I know what you're thinking. Wasn't this episode supposed to be about data science and, databases and all that other cool stuff? Well, ironically, we can't have that episode because there is an outage for electricity in the area. So our special guest unfortunately cannot make it today. But that gives us a perfect opportunity to reconvene and ask Tanmay some questions that we haven't asked him in about 10 or 12 episodes. So we're going to introduce our main guest, and then we're going to go right into the questions. Hello, main guest. How are you doing today?
Doing very well. Thank you for hosting this episode for me, Michael. I'm very excited, and as you mentioned, kind of ironic how there is an internet outage in the area where our special guest was supposed to be talking about data centers and how the internet works. But you know what? These things happen. It's technology. It's not perfect. It's especially shy when you want to show it off. What can we do? But still, though, really excited to get to answer everybody's questions. So, I mean, as Michael mentioned, feel free to go ahead and put as many questions as you can in the live stream chats, and we'll go ahead and get to them.
Alrighty, so we're going to start with the hard-hitting questions right from the beginning. Right over here, we have a question in chat from before we started from Akash. Welcome back, Akash. And Akash asks, what is your take on social media algorithms? And I'm going to say specifically any platform that doesn't use chronological orders for their posts, like Instagram, for example. What is your take on their algorithms?
So, okay, first of all, that's a very, very interesting question, and that sort of is a bit far removed from the world of tech and goes more into the ethics of distributing content at such large scales and what sort of that entails in terms of what what people think based off of that content, right? So I have a feeling that while I wouldn't be necessarily perfectly qualified to answer these sorts of questions, personally, I think that it's really a demonstration of how a lot of different techniques and implementations of technologies are really overfit to certain goals, right? So, for example, if you take a look at like Instagram, the way that they order their posts and the way that they'll only show you a certain section of your feed and then just go to like general cross Instagram posts, that is very much well suited for Instagram to earn money. That is very much well suited for Instagram to be able to show you lots of ads and lots of posts that they think you're going to like based off of your previous preferences, therefore therefore increasing your engagement with the platform, therefore being able to show you more ads because now they better understand your preferences, and it's just a vicious cycle from there. And I feel like a lot of platforms do this sort of thing now. And I think it's almost really difficult to work with because the situation's unprecedented. We've never really had technology or really media where where there's so much content that we're generating that there needs to be a way to be able to automatically filter through it and figure out what it is that you want to see. I mean, one of the, I think, famous examples was when you search up, for example, on Google, news about a certain political issue, based off of where Google thinks you lean on the political spectrum, they'll show you different results, right? Yeah. And so that continues to perpetuate bias because, again, there's the whole sort of, you're in an echo chamber sort of thing. But at the same time, I guess, in a way, it oddly makes sense because Google's using machine learning to understand what exactly you like. Right, it's sort of like it's hard to balance these things. You want great search results, but at the same time you don't want to be put in an echo chamber. It's hard to balance. But I would say it's half a technical issue and half a how do we choose content? How do we figure out what to show people? Because there's so much stuff, there needs to be some sort of way to show people things. But how do you do that with technology? Right? How do you figure out what unstructured content like natural language even means? I feel like it's just a really, really difficult challenge and something that we need to work on.
See, I'm going to step in and say I think TikTok does a really good job with their algorithm. I know everyone has their opinions on TikTok about like whether or not you're being spied on or something like that. But TikTok's like their front page, for example, is very, very simplified. There's following for the people that you follow, and then there's for you, which is curated using an algorithm to determine like what posts you might want to see next. And you have to remember with social media, whether you're talking about TikTok or Facebook or even WhatsApp, the goal of every platform, a lot of people think is like, oh, they're stealing your data. So they want to, figure out how old you are and what place do you live at and all these kind of things so they could sell it to other people. And it's not really that simple. It's not like they're trying to get your social security so they can send it off to some company. What they're really looking for is your time. The more time you spend on a platform, the more they can collect about you in terms of what you like and don't like, and the better the ads can be that they show you with respect to the likelihood that you'll click on them. So TikTok, for example, does a really good job of keeping people on their app. The For You page, like sometimes people have even, gone as far to test this because no one knows the algorithm. Mm-hmm. Like you'll be scrolling through the For You page and it'll be like, hey, if you're reading this, you're between the ages of 14 and 19 and you live in Ontario and you like tech and all these kind of things and all these sort of specific things. Like if you're seeing this on your For You page, chances are this is the kind of person you are. So people have made these kind of TikToks before to sort of test, is this how the algorithm works? And it does work like that. It's based on people posting in your area, so they're more likely to be interested in the things you're interested in, and they pay attention to what keeps you on the app the longest. And these are the things that they focus on as Tanmay was saying, to get the ad revenue and to show you better ads, is keeping you on the platform as long as possible so they can show you ads and see which ads work and which ones don't. But if you're like me, none of them work because I never click on any of them.
It's like, these companies aren't just these, really just nice entities that just want you to have good content that you want to see, right? It's not like, they have any sort of particular incentive to make it so you see unbiased content. They don't,
yeah.
Right? And all they want to do is make sure that you're on the app for as long as possible. And whether that is YouTube simply optimizing for watch time, so for example, not really caring what they're showing you, but really just caring about what's most likely to get you to click. You'll watch like one of those like really short, like 8-year-old 20-second YouTube videos that has like millions of views, and you'll go to the comments and everybody's there just because it was recommended to them. That proves that YouTube's algorithm is working. You clicked on it, so did millions of other people because YouTube recommended it to them. And YouTube's happy because they're earning a lot of money off of that. So that's definitely something to keep in mind. So a lot of companies already have a lot of data, and even if it's not like particularly because they want to know where you live, right? It's just because if they know where you live, they can better figure out what content to show you to keep you on the app in order to earn money from ads, and in Google's case, even show you specific ads and sell that information to the automated computer systems that are doing the ad bidding and millions of times a second, right? It's pretty incredible. It's like all these theories about they're putting microchips in the COVID vaccines and stuff. It's like we've already got TikTok and Facebook. Why would they need to do that? That's over engineering.
Right.
So.
Yeah. And before we get into the next question, just to add to it one more time, like having this, like people don't realize how important it is, like from an advertising perspective, to have information as simple as where do you live? Mm-hmm. If you look, for example, in the last Canadian election for our new prime minister, the entire western half of Canada voted Conservative. And that's where a majority of the Conservative votes came from. And when the election was over and the Conservatives didn't win, then there was this, I want to say big uprising. It wasn't like violence or anything like that, but there was a huge discussion with the western half of Canada saying, we want to leave Canada because we don't think we're being represented. And so me being, someone who's looking for advertising or whatever the case, I can probably guess that if you live in the western half of Canada, you're a Conservative and you voted Conservative and you may vote Conservative again. So this tells me what sort of political ideologies to think about when I say, here's a political ad. Do I show it to you or show it to that person? Mm-hmm. Right? When something happens and, someone writes a good or a positive and a negative article about it, which article do I want to show you as Google? Well, it depends on where you live, because you're more likely to like one over the other on just your location alone. Mm-hmm. So it's definitely all that, even the things that you might think they're trying to collect so they could like sneak into your backyard or whatever, it's all for the sake of advertising. And the next question we have for Tanmay, what are some new things that you didn't know until this year? What have you learned this year? And can you share some of those with us? How did you get to know any new technologies, tools, etc.?
That is a really fun question. And there is so much that I've learned. There have been times, and I've talked about this before, but it's actually kind of funny because sometimes, even just you and me, Michael, we're doing like a random problem, like a random coding problem. And through it, I'll end up learning something just completely arbitrary, something you'd be like, where did you ever end up learning that? And like 2 days later, it'll be super useful in another completely different project. And I'll be like, what if I hadn't done that random problem like 2 days ago? What would I have done? So there have been so many things that I learn with like every new project. One of the newest things that I've learned that I personally think is really, really fun is the different ways that Linux, Mac OS, and Windows do inter-process communication. So, there's a new project I've been working on. I think I've told you a little bit about it, Michael, and there's going to be a YouTube video about it soon, everybody, I promise. In fact, probably sometime this week. It has to do with Minecraft, actually, and building bots for the game. And also has to do with the fact that I don't really enjoy coding in Java. And so, I wanted to be able to build a separate component of the application in like Go or C or something, and then just have like the Java Minecraft component interface with my code. But of course, those are two separate processes. And Java runs through a JVM, so how do you even call native code, right? It's like it's layers upon layers of complexity. So one of the things I learned through that was, there was this way of doing it that I had already learned, which was using TCP sockets. And this is something I'd learned a long time ago, in networking. That's a pretty basic thing to learn. From there, though, I actually learned a little bit more about these things called FIFO files or named pipes, which are essentially not necessarily files, but references in the file system that tell the kernel when two processes attached to this thing allow them to share data through memory very quickly. So it's much faster than, not much faster, usually faster than a TCP socket, but it's still pretty slow. And so I had later learned, actually quite literally just this morning technically at like 1 a.m., I was learning about shared memory, which is quite literally just saying, hey, I'm C code, I have a memory buffer over here, tell the kernel, stop protecting this memory buffer and allow other processes to access, read and write from this memory buffer. And that is insanely fast compared to all of the other approaches. And all of these things that I learned, these are super, super like technical and down in the weeds of like kernels and like very specific platform architectures. But the moral of the story, I guess, is that a lot of these things I learned, not because I sat down one day and said, I want to learn about inter-process communication, but rather because I said, you know what, I want to build this thing. I want to build a bot in Minecraft. And well, I don't like Java, so I like Go. I want to write it in Go. How can I do that? Right? And I started thinking, well, there's separate processes. What if they could communicate? And that led me down into the rabbit hole of IPC. So I would say that really a lot of learning is learning by doing, because that's like, the number one way to learn anything is to come up with a problem and try to solve that problem, architect the solution for it. That's just one of the many examples. A little while ago, I was working on some neural networks, and I was learning about the Apple neural engine architecture, right? So a little while ago, I was working on taking my auto lyricist project, the music lyric generator, and porting that to work natively on Apple Silicon to run on the new neural engines. Issue, of course, being that Apple very heavily locks down the neural engine, so much so that it's pretty much up to Apple's luck if your neural network will run on it in the first place. You can't really control that. You don't know what kinds of layers will run, what kinds of layers won't run, if they don't run, why they don't run, what to replace them with. You don't really know anything. So, I was watching a video from this guy called George Hotz, founder of Comma AI, great guy, well, a very smart guy. And he has, this video series where he's done like 4 consecutive 14-hour live streams just trying to decode the Apple Neural Engine's instruction set. So trying to port your models like literally instruction by instruction to the neural engine. And again, what did I tell you? It's not because I sat down and said, I want to learn about the neural engine. It's just because I said, you know what? I want to build an on-device lyric generator, and that just happened to be the best way of doing it, or at least the most fun way of doing it. So, there's all these things, and I guess all of it boils down to really just having a problem, wanting to come up with a solution, and going through it step by step, and really changing that North Star metric along the way as you learn different things.
That's a very long answer. No, but it was a really good one, and everything you're saying was on point, especially like with the Apple Neural Engine. I just think of that SpongeBob meme where he's like, "Nah, I don't really feel like it," and he just
Exactly.
lays over. It's this machine learning code that only works on a 3090. Let's try to get it to run on the M1. It's like, I don't really feel like it. Definitely, we've seen how, especially with some of my computer science classes, it's like we'll just learn about something and then somehow it just immediately comes up in a completely separate problem. Like,
Yep.
I mean, Tanmay's known this for years, but I was learning about like hash maps and stuff like that, like actually implementing them in Java. And then not long after, we get a problem, and Tanmay's like, just use hash maps. And it's like, you know what? That's in my toolbox now. So actually, that is possible. But and before that, I had never heard anyone say like, "Oh, just use a hash map to solve the problem." There's always been some different way of doing it.
Yeah, exactly. And one of the things that I love so much about computer science is that ability that you have to just extrapolate concepts and think, if something doesn't exist, something like this should exist, and then try and figure out if something like that actually does exist. I still remember.
Remember when I invented merge sort?
Yeah, well,
we'll get to that. Yeah,
yeah, we'll get to that. But there was this one really funny thing. One of the I don't remember much about back when I was like 7, getting into the world of programming, since that was a long time ago. I think 10 years ago at this point. But still, one of the things that I remember very clearly was I was building an application. It was just like a facade for like credit card payments. It wasn't like an actual processor. Obviously, back then Stripe didn't exist, and I didn't know how to call these APIs. But it was just like a little screen where you could enter your details and it would do something. So one of the things that I was wondering is, you can create variables to store information, but what if you wanted the variable name to also be chosen by the user so that they could then access that again in the future? I was like, something like that has to exist, and I was thinking of dictionaries and hash maps. Right, and so I would ask my dad, but the thing is, back then I didn't really know how to communicate that concept clearly enough. I was like, something like that has to exist, but I don't know what it is, right? And so later, when I was learning Swift, I was like, that's dictionaries.
It's like the meme of the guy with all the papers on the wall and the string connecting all of them, and he's just like, guys, what if you can name the variables?
Exactly. So yeah.
And yeah, the story of inventing. So I had an assignment, and the assignment, I think the question was, you're given 4 numbers of any input. And I just standardize it to a list because you're getting numbers. And they said you're giving 4 numbers of any input. You have to write an algorithm that'll sort them in no more than 5, I believe, comparisons. So you have to sort the entire list of numbers using at most 5 comparisons. And I did it in one, I think, used 4 every time. And I sat there and Tanmay knows, I started on paper. I was like, all right, give me a list of numbers, like give me A, B, C, D, where only you know what those numbers mean. And I'll ask you a set of questions, see if I can sort A, B, C, D. And I was on paper, I was doing math, I was doing all these different things. And eventually I came up with an algorithm that worked for everything I gave them. And I was asking like, okay, give me a list. And then the program would sort it. And I figured it out. I said, Eureka, I threw the papers in the air, all of that stuff. And when I sent it over, immediately someone was like, that's merge sort. I said, what? That already exists. It's called merge sort. Oh, well then. I totally didn't spend 4 days on that.
Yeah, actually, perfect example, just really quickly before we move on to more questions, because I know we have a lot to cover. And also, thank you, everybody, for sending in questions, and we'll be sure to get to them. One more thing I do want to say is, when I was writing my first book, Hello Swift, one of my application examples was actually an Apple Watch app that would be basically just a number guessing game. Internally, it would have a number, and you would, guess the number. And back then, I didn't know things like binary search existed. And I was like, what is the optimal strategy for winning the number guessing game? And I drew it out on paper, and I was like, well, if you guess in the middle, then you can see if it's greater or lower, and then you can go into the middle of the middle based off of which section it's in, and then you can keep doing that. And then I searched it up, and I'm like, oh, that's just binary search. I reinvented binary search.
Oh yes, these people 40 years ago did this.
So
that's the great thing about computer science, though. It's because you're rediscovering every time you learn it. So you're always going to get to that moment where it's like, oh yes, people 40 years ago came up with this thing. Exactly. And I just came up with it again. Yep. All right, but Our next question is from Cash, because they say that their previous question about social media was incomplete, and it wasn't the real question that they were looking to ask. So their real question is, what is your view on fake news and controversial negative topics spreading more quickly than real and positive news on social media? So basically, fake news and controversial topics, and how can technology be more optimized to prevent this?
Two things. First of all, it's not a technology problem. It's a financial problem. It is. It's
Hello,
an issue.
I like money.
Exactly. So when you go to an Instagram exec and you ask, why did you choose to show this ad? I like money. No, the Mr. Krabs, I like money. So no. So we're only half joking when we say that. But yeah, the idea is, first of all, it ties right back into what we were talking about before. It's not a technology issue. We can easily create technology to only show the most positive, uplifting news in the world. Whether or not that's of any value, again, is also debatable, but it's possible.
News, 12 puppies born today.
But then from there, also keep in mind that despite the fact that this is a financial issue, a lot of the way we sort of look at this is as a technology issue. And so maybe the greatest video I've seen on this topic ever is a video from this great YouTuber. His name's CGP Grey. He has a great video called, I think it's called Thought Viruses. And he sort of makes the analogy of different news articles or concepts or ideas being viruses. And if an idea provokes emotion like anger, right, or fear, or despair or something, it generally lasts a lot longer in your brain than something that's happy does. And guess what? If the thought's still in your head, then you're still on the social media app and they're still earning money. So they're only going to show you the things that really get you angry. And the thing about these thought viruses is that they can only exist if there's a completely different thought virus infecting a completely different group of people that hate the other group. So really, when you have these two sides of like an argument on social media, the fact that they're so big really just makes the argument worse, right? I think it's really good to go ahead and watch CGP Grey's video on, thought viruses and fake news and controversial news and social media and how this is all structured. I think it's the best sort of description of this whole thing so far. But overall, I think the best way to go about solving this is to not treat it as a technology issue, but rather treat it as more of like a societal and financial issue, really. Which is, again, why I don't think I'm the world's most qualified person to answer this question. But still, it's definitely really interesting to look into.
Yeah, absolutely. A lot of people think that because it's on a technology, then the solution is more technology. That's kind of how we just handled everything. But as Tanmay was saying, like, you get attached to negative things. And when you hear negative things, it's pretty well understood that you weigh positive and negatives at about a 10-to-1 ratio. So for example, if you walk into a room and you say, I have this nice, cool outfit, I think people are going to love it. And you have one person say it sucks, that's going to weigh on you about the same as 10 people telling you look great today. So it's when you hear negative news, it weighs on you much more, and you're much more focused on what's going on, and you want to be glued to the screen and paying attention to what's happening. Yep.
If you can't solve one medium LeetCode problem, that's the same thing as solving 10 hard ones.
And that's what it comes down to. It's less of a, because there's always been fake news. This is not a new, like a lot of people think with the rise of deep fakes and stuff that it's suddenly we have a fake news problem. We've always had a fake news problem, right? Something as real and as old as 9/11, which is 20 years old this year. Even 20 years ago, people were saying, oh, this is a hoax. This is whatever the case. We've always had this issue of people not believing what is real and what is fake, and people trying any major thing that happens, people are trying to debunk it and say this didn't happen and whatever the case. And so this idea that suddenly fake news is on the rise and, stories are being made up, this is not a new idea. And technology isn't really it's really just shifting. It's not making it worse. It's not really making it better. It's just suddenly, you know, a lot of people with the tinfoil hats, instead of just saying, oh, they're aliens, I swear, they can make videos of aliens in the sky and say, look, there's the aliens I was talking about.
And they now have the platform to connect with other like-minded people very easily, no matter where they are on the globe. And that's a very good thing and a bad thing, right? It's, in a way, it's a very good thing, because as a developer, if I'm really interested in some exotic thing, like yesterday I was taking a look at this thing called the Barrelfish operating system, which, by the way, is my favorite new OS. It's by a research team in Zurich and Microsoft. And you know, incredible OS, and I can connect with other people who also love it, regardless of if they're in China or India or Argentina. But you know, that also gives a lot of people that maybe aren't on the right path, also the opportunity to connect with lots of people. And in a way, that's a bad thing, because then they're spreading a message that shouldn't necessarily be spread. But at the same time, that also digs into the question, what kinds of messages shouldn't be spread, right? It's a whole...
Who decides?
Exactly. Who gets to decide that, right? Like there's all sorts of things. Like there was this one, you know, just sort of last thing we should mention on this question. You know, you mentioned that 10-to-1 ratio. There's generally fear with everything, and I feel like fear also sort of ties into that 10-to-1 ratio. Like, for example, when I think it was the Pfizer vaccine, when it was first sort of announced, there was that one news article of, oh, 4 people that were vaccinated developed this kind of facial paralysis. But
I saw that.
Yeah, but if you take a look at the percentage of people that developed the facial paralysis to the total number of people that were vaccinated, and you compare that to the total number of people that developed the same disease just normally in the world, there's a lower percentage in the vaccinated population.
Yeah.
Like, there's fewer people than there should have been in that population. It was just a statistical anomaly. But still, of course, there's going to be all these news articles being like, oh, don't get the vaccine, it's you know, facial paralysis, whatever. And then similarly with Facebook, right? They're going to be like, oh, Facebook made 2 AI bots that were communicating with each other in their own language, and we had to shut them down. That's not how it works, right? It was a simple gradient descent exercise of optimizing the input vocabulary to the models. And obviously the point of that was to generate another language. And obviously we couldn't understand it because it was mathematical. So, you know, it's sort of, it can be hard to really get what is real. But that's just how social media is.
Yeah, statistics is hard. Like, ask anyone with a PhD in statistics, they'll tell you statistics is hard. It's never that simple.
If I remember correctly, I think statistics, if you take a look at its etymology and you go back to, like, I think it was Latin, one of the words that it derives from is liar, if I'm correct. So, I don't know.
But so if any of you play, I know Tanmay plays Minecraft, so if any of you play Minecraft and you've heard about the recent speedrunning, I don't know the word for it, the whole thing going on with the speedrunning community because of the speedrunner Dream, who people are saying, you know, faked his numbers, modded his game slightly so that he can get better luck. And there are like so many statistical papers about what is the likelihood of him having this kind of game, and people going back and forth with their study of statistics. And there are math YouTubers, I've seen videos of math YouTubers who have PhDs reading into these stats papers, and they're still like, yeah, but it's not that simple, kind of thing. So, and statistics can easily be used to give you any piece of information and make it sound good or bad. So it's all around just not a simple, here's the technology we can use to fix it. A lot of it just comes down to things outside of the scope of tech, like the human brain and how we work, statistics, all these other kind of things. Our next question, we're going to have to start speeding up and catching up here, is from Momin, I believe I'm pronouncing that right. Kindly tell us what are the important technologies that people need to know as newbies in computer science, which will affect their future learning.
Ooh, okay. So you're new to computer science, what topics you should learn? I will say the key thing that I would recommend for people getting into computer science is start at a high level, but the low level is more important than you think it is. And what I mean by that is, you know, one of the sort of default languages that people will learn when they're getting into the world of computer science is Python. And the reason for that is pretty simple. It gives you a good sort of understanding of different logical concepts of programming, but at the same time, you don't care about the fact that you're using a computer, right? You can be like x equals 5, x equals Tanmay, x plus Michael, and it'll give you Tanmay Michael. It'll forget the 5 ever existed. And Python just sort of does these things because of the way it's built. And so it's great for beginners, but something that I think is really important is as you continue to build software, what becomes really, really important in the world of computer science is extrapolation. Right? That is something that, I've said it time and time again. Extrapolation is how computer science is done because you're never going to know everything. You need to be able to take things that you know and some sort of problem description and somehow take what you know and mold that into what you think the solution should look like, even if you've never seen some certain components of that solution before. If I wanted to build an application that can automatically determine video quality in like a Zoom meeting and tell me if it's wrong and tell me what's wrong, even if I've never built one of those components before, maybe if I've never done computer vision before, I should still be able to say, all right, generally I understand the architecture should consist of getting the video input feed, feeding it into a system that's able to detect quality, feeding that into a system that's able to give corrective measures, and then show that to the user. In order to show that to the user, I would then be using the Cocoa APIs, or I should be able to come up with this sort of high-level architecture. So start off by learning logical sort of skills, right? Use a language like Python or Julia. For example, you can use my book, Tanmay Teaches Julia, or rather, not or. And then from there, once you learn the sort of logical thinking skills, get into something more low level, C++ or C. And the reason I say that is because that's going to give you an idea of how computers are architected. Once you understand that, you'll be so much more capable of extrapolating what you know and your toolkit into new problems. So I think that's really important to keep in mind.
Yeah, Tammy knows how long it took me to wrap my head around pointers because I had started with Python for like a good 3 years, 4 years.
We still
and it's not even that. Yeah, and it's not even that I don't know the concept. It's just I always get confused as to when to use the star and when to use the ampersand. And it's like, okay, if I'm making a function and I'm passing something in, when do I, pass in the pointer of the value versus or pointer of the variable versus like the actual value and things like that. So it's like, yeah, I completely understand how pointers work, and I fully understand like why you'd want to use it. I just never know when I'm supposed to use this symbol, that symbol. It wraps around my brain because I'm so used for like 4 years of just, oh, you have a variable, give it to your function, it's fine. So before we get into our next question from Shiva, we had a comment from Mystery King that said the future of technology depends on human, not on money. And I'm just going to say, I'm sorry, but I completely disagree. I think that, humans, especially people who very much enjoy technology and coding, they don't have that want and that need to go and do things. But at the end of the day, what gets decided as to, where the industry moves is based on what makes the most amount of money. When you look at the phones we have today, we have smartphones now, right? And technology has come such a long way from the very first iPhone in 2007. But if smartphones weren't really making money compared to just regular dumb phones, then people would have stopped making smartphones. And we wouldn't be living in a world with smartphones today. And I think I can go on for forever examples, but I want to get into the next question. But I personally believe the future of technology depends on money. And obviously there are people who need to be behind that money, but it's about what makes sales and what doesn't, because that's how a company decides whether or not we can keep investing in this. If Apple's new M1 laptops didn't sell that well, and their M1X and their M2 just continue to not sell, as incredible of a technology as they may be, Apple might just have to stop making them and go back to using Intel, because the future of technology has to be where the money is, because at the end of the day, Apple needs to make that money. As rich as a company as they are, they still need to make profit at every single quarter. But our next question is from Shiva. It's a load of questions, so we'll see if we can go through them one by one. Shiva first asks, what are your plans for 2021? And are there any projects that you're working on?
Very good question. All right, so my plans for 2021, I gotta say, it's kind of hard to say because things change every day, especially in the world of technology. Like things change extremely rapidly. Generally, though, my plans for 2021 are to really, as much as I can, scale up a lot of the initiatives that I have been working on. So for example, when it comes to educational content, luckily my new book, Tanmay Teaches Go, is actually being published very soon, sometime actually within the next couple of weeks. You will be able to get your hands on physical copies of Tanmay Teaches Go, which I'm very excited about, as well as, you know, entire new video series and courses that I'm working on that I can't talk about just yet. But, you know, Michael, you also know about some of these, and these are videos that I'm sure we can both vouch for will be very exciting to watch and very fun to watch. You know, you've already gotten a little bit of a sneak peek earlier today when I talked about the whole Minecraft and building bots and things. So keep that in mind. There are a couple of really interesting projects that I'm working on already for 2021, as well as a couple of very also interesting new technical projects. For example, again, earlier this year, I talked about auto lyricist and music lyric generation. I'm also working with another company now out of the UK on the world of music too. So really just working on applying my technology that I build in a lot of creative fields, which is something that I'm very passionate about now. And of course, continuing to build some really interesting projects in the world of communication is how I'll call it, with one of my mentors as well. So again, I can't tell you exactly what these projects are, but you know, applying technology in creative fields, communication, building new YouTube videos, courses, books. That's my goal for 2021, is to scale up all these initiatives as much as I can to really, you know, give back to the community. So that's what I'm working on.
Yeah, so my plan for 2021 is to pass my classes. No, you guys see, as always, I'm giving you guys the exclusive scoops. That's what I do. We have Minecraft bought something around there. We have the Go book. As always, I give you guys a sneak peek. That's what I do. We'll squeeze more out of him this episode. Don't worry. It's definitely, I can tell you guys from, you know, having the sneak peek on some of these things that Tanmay is working on, it's going to be a great year. Absolutely. And we're working on some really great stuff for everybody. Our question is going back up a bit in some of the questions. This one is way too technical for me to understand, so I'll just see if it makes any sense to you. Someone asked, after building a deep learning model and converting it to T-Flight, I believe that is, for easy development to edge devices, does that hurt the accuracy? If yes, how?
T-Flight. Okay. Well, I'm not sure if you're referring to. Is it like how's that spelled exactly?
TFLITE.
TF Light. Okay.
Okay.
Not T-Flight.
They should
like
put a
T-Flight.
hyphen or something. TF light. Okay, everything has a light version to it.
Yeah.
What is it? TF Pro,
so
right?
when you said T-Flight, I thought you meant like Apple Test Flight, and I was like, why would you deploy a deep learning model to Apple Test Flight? No, so T-Flight. Sorry, yeah. TF Light, not T-Flight. TF Light is TensorFlow Lite.
Okay.
And the way you deploy to TensorFlow Lite will sort of mold your accuracy of the model. A lot of models, especially computer vision models like ResNets, don't really care about the precision of the weights. Like you can literally go from float 64 to int 8. And a lot of these models will not care if you remove that precision. They just need an overall, like, overarching resemblance of the original weights, and they're good to go. As a matter of fact, the vast majority of the weights aren't even really used. You can prune them away. So in theory, nothing should go wrong. You shouldn't be, you know, sort of in any way majorly affected in terms of accuracy or precision. However, again, gonna say take that with a huge grain of salt. It depends very much on your model. The average model will not care. However, lots of models may. For example, if you have a more sort of audio-focused, time series-focused, natural language-focused model, these are more prone to errors when you reduce precision of the models. Quantization shouldn't affect it at all. Oh, sorry, no, this is quantization. You know, the sort of compression that TensorFlow does shouldn't affect this at all, and also just the mere sort of act of converting a TensorFlow model to a TensorFlow Lite model does not affect accuracy either. It's only when you introduce certain optimizations like quantization that you start to affect the accuracy, which you could even do without TF Lite theoretically. So TF Lite doesn't really change anything here. It's the optimizations that you introduce along the way. If you quantize your model, if you prune your model, these are things that can reduce accuracy. So in my opinion, best way to go about this is take your model, run those optimizations, then refine tune the model once more on the data set just to make sure everything's working well. then go ahead and actually deploy the model. So I think that's the best way to go around doing it.
In my defense, it was spelled lowercase entirely, one word, TFLITE. So I said, okay, T-flight, that makes sense. So someone asked, we have Astronomy with Manas. That's a familiar name. Welcome back. They said, question, what interests you both other than coding? I'll let you go first because I want to know this one.
I just threw a null pointer exception. No, no. I mean, there's quite a few things that I enjoy apart from coding, even if coding is my number one.
Long walks on the beach.
No, apart from that, there's biking. I like biking. Haven't been able to do it in some time, unfortunately, because COVID. And plus, it was winter in Canada and cold. I don't like going out in the cold. But that's something I enjoy. Table tennis, I really do enjoy. So I have a table tennis.
Yes, he really does.
Yes, I do. That's something that I really enjoy. I think we've been able to play table tennis before at the lab. So yeah, that was fun. Before COVID, we could actually do that. So yeah, that was fun. Apart from that, watching TV shows, you might know that SpongeBob SquarePants is my favorite TV show easily. That's definitely fun. There'll be lots of times where Michael will make some kind of obscure SpongeBob reference. Don't know exactly what scene of what episode that was from, and so yeah, that's also definitely really exciting. So apart from coding, I would say watching TV like SpongeBob, table tennis, biking. Those are some of the things that I love to do. What about you, Michael?
Tammy, he's a very interesting character for sure. I'm going to see if this explains my answer as simply as possible. I think everyone will get the idea. Yeah. I have 2 monitors and one of them is an ultra wide. So definitely, for as long as I can remember, video games. Yeah, definitely outside of coding. Video games are what got me into coding in the first place. I'll give you the story. It is one of the funniest rabbit holes of my entire life. I had a laptop that was really old. It was a hand-me-down laptop. And I used to watch these YouTube videos of people playing these games like Gary's Mod, Arma 2, and I really wanted to play them. So I tried to just download them on my computer and run them, but I realized that computers don't all work like that. And I was about 13 at the time, and I was only used to like consoles and your Xbox and stuff. And I tried to load up the game and it was always crashing and stuff. So and when games I got to work, I was only getting like 15 FPS at the best. And so I was searching it up and I figured out like, hey, my computer doesn't have enough RAM. This game needs like 4 gigs and I have like 2 gigs. So then I started Googling like, how do you get more RAM? And I was actually downloading this software that was like, yeah, you can download more RAM here. And at one point, I was basically trying to use swap memory. I had no idea what I was doing, but one guy made a video about how you can increase your RAM by using your hard drive as RAM. And again, this isn't SSD, this is hard drive. And so it's incredibly slow. And he's like, yeah, just go into your Windows terminal, enter this command, and suddenly your hard drive space is RAM. And I was doing that and I was like, okay, but why is it still not working? And in a year, I always like to tell people in the matter of a year, right? From grade 7, I was in to about the end of 8th grade. In a matter of a year, I was able to go from trying to download more RAM to get games to run to building my own computer and understanding that you can't just download RAM like that. Video games absolutely have been a very important part about me getting into development, but even today I still very much play them, and coding has kind of really just helped me get a better understanding of video games. So I appreciate them more. I help people, I can play test certain games and understand from a technical standpoint what they need to change. And yeah, it's kind of just like this meshed relationship of like games got me into coding and now coding helps me stay updated on games and vice versa. Yeah.
Very nice.
Next question. I think I'm getting a phone call, so let me just decline that. Next question. Someone asked, and this is me coming at it with the sneak peeks. Akash asked, can we get a glimpse of Tanmay Teaches Go, its index? I'm assuming table of contents.
that may already be available online. I would need to check, but I can give you an overall sort of arching view. You know, the idea of the book is that you already know how to program, like you've coded in some sort of language before, and that Go is a new language you'd like to pick up. We start off with a chapter introducing you to the world of Go and why you'd like to learn it in the first place. Moving into a sort of overview of the Go syntax, sort of telling you the sort of correspondence between all the general programming concepts you may have learned and how they're represented in Go. So things like loops and conditions and functions and these new things called Go routines, all kinds of things, modules, and how they map over to Go. And then from there, implementing different kinds of applications using, you know, these sort of common data structures and algorithms that you would apply in the real world to learn Go. So things like implementing Dijkstra's algorithm, Conway's Game of Life, implementing an application that plays Tetris automatically using Swift and Go. So lots of really fun stuff. So again, please do stay tuned for the book. There is actually already a link in the description to where you can go ahead and pre-order, and you may be able to find a table of contents there. But if not, as soon as I can post an actual table of contents, I will go ahead and do that.
Yes, see more sneak peeks as always. This one's from I hope the name I'm pronouncing it right, Dave. You might have noticed the pattern. I'm really bad at pronouncing names. This one's from I believe it's Dave, who asks, "What do you think about differential programming, complex analysis? There are way too many machine learning experts now. Which fields should we focus on to get a job?"
Well, I would say, first of all, about your point of there are too many machine learning experts, I would say there's too many people in machine learning, but not enough machine learning experts. There's a difference, right? And that's the same difference between people who write code and people who are software developers, right? There's that gap. And that gap is, you know, I think Joel Spolsky, I forgot the last name. He described it perfectly. We've actually brought this up in the previous AskTanmay. He wrote this one article, you know, back in 2001, like 2 years before I was even born, and it's still relevant, where he was complaining about how, you know, modern programmers, even back then, are just very prone to implementing problems like, for example, Schlemiel the painter algorithms. And, you know, it's a relatively obscure thing, but like, for example, in Excel, if you were to have a single cell with a really long string, the program would crash. And the reason for that is because Microsoft is making a lot of, or Excel rather, is making a lot of unnecessary calls to the string length function in C. And that function, you know, if you didn't know, in order to find the string's length, it needs to start at the beginning and keep going character by character until it reaches the end of the string where it sees a null terminator and it's like, oh, so that's the length. And that is slow. That is really slow. And because you have to go through the whole thing. And so, you know, there's very easy ways to go about solving this, like for example, using Pascal strings or even just simply caching the variable. But they don't do that. And a lot of the reason is because, you know, new programmers don't understand these sorts of low-level things very well. And then we have bugs in Microsoft and Adobe software that is supposed to be, you know, like mission-critical, reliable sort of thing. And so what I would say is, you know, just like how there's lots of people who write code, but not very few, but relatively fewer people who really develop software and understand how things work at a low level. Similarly with machine learning, there's lots of people who can spin up Keras and PyTorch and pop together a neural network. But there's not very few, again, but there's relatively fewer people who can actually say, you know what, this architecture works because of this. And so therefore, because I have this new problem, I'm going to be using capsule networks as well as mixture Gaussian networks in order to develop a distribution of where the next point should be on screen. Right? You know, being able to understand the lower level details and come up with brand new architectures is something that not that many people can do. And if you're in an area where there are too many people like that, that just means the area you're in is oversaturated. You might live in some sort of like, you know, city where there's just tons and tons of machine learning experts. I don't know the exact details, but, you know, stereotypically, I guess you could say, like in Silicon Valley, I'm sure there's way more machine learning engineers than there would be in, like, you know, some random rural
there's no yearly convention for this. You guys, machine learning experts don't all just meet up and just expert together or something. I don't
Not allowed to say. But
know.
then we get all the ritual robes and everything. No, but yeah, that's the idea. So I would say that it really depends on the market and the area that you're in. But also going to your second question, if I were to go ahead and see here, which fields would be the best to focus on, I would say the way you can differentiate yourself as a machine learning expert is really um, think about applying machine learning with domain experts. Because technology in general is really meant not as its own industry even, it's meant as the backbone of every other industry. Everything we do is powered by technology, no way around it. You go to a fast food restaurant, that whole chain of getting the food to you is powered by technology. From the trucks that got you the food, to the factories that manufactured it, to the people who came up with the recipes using the help of their tech, to the people taking your order. Like, it's all powered by technology. You have to keep that in mind. And so I think it's really important to then go ahead and realize that, especially with machine learning being the sort of hyper-personalized technology, you have to be able to really work with domain experts in order to get anything done. So as a machine learning expert, having experience actually working with domain experts in a wide variety of fields and being able to understand their field enough to know how to implement the right algorithms, and being able to explain to them the capabilities of technology enough for them to understand what kind of data is important, I think that's missing with a lot of ML engineers. And I've met with a lot of people that know machine learning, but they simply cannot use it in the real world just because they don't know how to interact with domain experts. Just a couple of days ago, I was on a call with someone. This is for one of those 2021 projects. And they were talking about how we want to predict these different attributes of like a song. And I was like, yeah, that's relatively, I can do that. I've done similar things before. But they had this sort of doubt in their mind of, but then wouldn't you have to build a separate system to predict this attribute and then a separate one for this one? And I was in the back of my mind thinking, oh wait, they don't really know how neural networks work. And I was like, no, that's not how it works. With neural networks, you can build a single network to predict both attributes. And they were like, oh, that's great. So we only need a single network. And so it's really important to keep in mind that bridge. I think that is the most fragile area of machine learning today, and that really needs solving. So I think really focus on that. Also, really quickly, I do want to cover the differential programming aspect. Differential programming is a huge passion of mine. I love the Swift for TensorFlow project, right? Michael knows this. I was distraught when they said they would have to archive it, but another.
He didn't sleep for a week.
Yeah, that's an understatement. No, but really though, it is a great project, and so Julia easily takes its place. I know that Facebook actually is working on something similar to Swift for TensorFlow, but for Kotlin. And I know it seems kind of weird, like why is Facebook research working on an IntelliJ language that Google uses for Android to implement differentiable programming? But that's the beauty of open source. IntelliJ or I think it's called JetBrains or whatever the company is. I keep mixing up their IDE names with their company name, but I think it's JetBrains. They can build a programming language which Google can then use for Android development, which can slowly replace Java, and Facebook research can modify it in order to support differentiable programming. It's incredible. So Julia, Kotlin, Swift, these are great languages for this sort of thing. In complex analysis, I don't really, I haven't personally done too much research into that. So again, I don't think I would be the greatest person to comment on the world of complex analysis. However, once again, in this sort of bracket of scientific computing, sort of that umbrella, complex analysis sort of really fits into that, and Julia is a great language to use for scientific computing. So that's sort of how I would say it's important to work on machine learning in the next few years.
Yeah, and I'm in engineering, so the only differential I know is differential equations. So with that being said, our next question is from Hamad, who asks, any major changes that you see coming into the field of data science? Are there any new tools that have the potential of replacing widely used tools that already exist?
Ooh, I would say the world of machine learning is a lot more mature now than it was a couple of years ago. When Swift was originally announced, of course, Apple didn't really have all that much experience creating their own languages, and the ones that they had made were not the greatest to say the least. Uh, yeah, I mean, take a look at Metal or take a look at Objective-C. We can all agree they're not exactly the most elegant languages in the world. But they were very good at designing APIs. I'll give them that. Like their API design is second to none. Like the same old APIs that have been powering macOS GUIs since like the original OS 10 are still in use today with very few deprecations and new functions. And they're still like very, modern and relevant and high performing. So they're good at designing APIs. But when they designed Swift 1, not exactly the greatest language. There were pretty simple bugs, like you could define an array as a constant, but then you could still append to it. I remember all the old syntax glitches, and they were really fun. But then slowly, over time, Swift 1, 2, 3, and 4, they fixed all those bugs, but that introduced major changes to the programming language, to the point that Swift 1 code is essentially a completely different language to what we have today. And so a lot of people were like, why would we use Swift if it's changing every year? But then Apple was like, okay, we're going to slow down on the changes. We're going to introduce application binary interface stability, and we're going to do this the right way now. So they sort of matured down, and now things evolve more slowly. I think the same thing happened within the machine learning community, where at first we had like the Theano library, which was, again, not exactly the greatest. Then we had TensorFlow 1, which was like, you know what, there's nothing else, so we got to use it. Then we had PyTorch, which was like this breath of fresh air, and everybody, sighed a collective breath of relief and was like, finally, no more graph building. and, and there was a light at the end of the tunnel, and all these researchers started to use, the PyTorch way of building neural networks. And then after that, TensorFlow was like, we also want a piece of that cake, and then TensorFlow 2.0, which is even better than PyTorch. And well, it depends on what you're building, but in a lot of cases can be better than PyTorch. So I would say that today we've seen the sort of evolution and convergence of pretty much every toolkit to almost be the same thing. Where like in TensorFlow, you have pretty much all the features of PyTorch, and PyTorch has pretty much all the features of TensorFlow with some minor differences. So now the difference is sort of like almost the difference between using like PyPy and Python. Not a great analogy, but using PyPy and Python. They're the same thing. Maybe there's a couple of differences, but they're the same thing. So again, they can be implemented completely differently in the back end, but in the front end, not really all that different. So I would say that in terms of new toolkits, I don't think today there are any promising new, at least brand new, deep neural network toolkits that are promising to, completely replace the ones that we already have. I would say there could be like a couple, like for example, I think CoreML over time is going to generally be more dominant on iOS devices, for example, than TF Lite. I could say that I think overall, this isn't within the world of deep learning, but within programming, Kotlin will slowly but surely eat into Java's market share and replace it. A man can hope. And similarly for things like Swift and Rust against C. So while there are general trends, I think the industry has matured enough and there's enough enterprise level code in the field that people don't want to change, right? Before, when it was just research and people doing science, they were like, every paper can be a brand new language or framework because we don't care. We're just building code and making sure it works. That's it. But now that enterprises are like, yeah, we like machine learning, now that they've actually deployed things, it's harder for everybody to shift. So the research community, they're still using PyTorch. The real world, they're still using TensorFlow, and I don't think that's going to change for a long while. So, of course, there are some new, applications. Like, for example, there's Julia, right? And we can hope that in the future more people start to adopt Julia. But as of right now, I don't, in the very short term, see anything completely overtaking what we already have, kind of like PyTorch did TensorFlow a couple years ago.
All right, and the next question we have is from Shiva, who asks, how many hours in a day can you do just coding without any break? And I think the real question should be, how many hours in a day can you be doing anything without taking a coding break?
That is the perfect way to put it, because anytime you call me, it would be profitable for you to bet money that I am coding if you were to call me at any arbitrary point in the day. So, I guess Michael put it very very well. I guess it's 20 to 30 minutes before my coding withdrawal symptoms start. No, so I guess it really depends. I really enjoy coding. Just yesterday while I was working on that Minecraft bot I was talking about, I was actually recording myself doing that, and I think I went like a good 4, 5, maybe 6 hours just implementing inter-process communication. First the TCP sockets, those didn't work. Then the named pipes, those didn't work. Then started working on shared memory, and that's a thing that I'm learning about now. So, I guess it really depends on the day, what stuff I have to get done, what sort of stuff I'm really excited about. Like, for example, even if there's nothing really due, but I'm just like, oh, that would be a really interesting idea. I'll just spend like a couple of hours sitting down doing nothing, just coding that idea. There's one time I was traveling and I just finished a keynote, and right after my keynote, I was like, that's a really interesting way to calculate pi. And then when I went back to my hotel room, I was like, I just spent the rest of the day in the hotel room implementing this new pi calculator, and getting it to run on CUDA and all these things. So, it's honestly just however long I feel like it that day. But
if any of you have seen, sorry, I just want to say, if any of you have seen Deadpool 2, with he has this one scene. It's like he flips a coin. He's like, heads, you did it for me. Tails, you did it for me. And he flips it. He's like, I don't have to look. You did it for me. And that's basically Tanmay with code. It's like heads, he's writing code. Tails, he's writing code. I don't even have to look. He's writing code.
Actually, funny little story is, Michael, you remember that I've only really participated in one hackathon before. I've judged a couple, and I've attended, been moderator a couple, but I haven't really attended one. But I did do this one, and I think that was like a good 48 hours of just consecutive work. Like, it was, wake up one morning, 9 a.m., go to the lab, work till like 11 p.m., maybe take a 1 hour break, go back home, eat, whatever, and then all throughout the night, and then all throughout the next morning, just continuous coding and building out an entire software solution. So there's honestly no limit. It's just how much, I mean, at least for the case of the hackathon, how much Pocky I can manage to eat in the middle. So I guess it really depends.
Yeah, back in the in the office at IBM, you walk into the office at like 7 in the morning. You want to get there early, and you see Tanmay in his office just coding, and it's like, bro, you're really working hard at that hackathon. And he's like, hackathon? Like, what hackathon? No. So yeah, definitely he really likes the code. For those you don't, that you're hearing it live, he really likes it, which is fun. He's really good at it. So we have Swarna Deep asks, can you please tell us what is your beast machine in which you code?
Ooh.
I want to hear the specs officially.
Well, it's a MacBook Air M1, 16 gigs, 8-core GPU. And I know that doesn't sound like a beast, but believe me, it is.
It
Michael,
really is.
Michael, you can vouch for this. You recently switched from a 16-inch MacBook Pro to your 13-inch MacBook Pro with the M1. And, Michael and I, we have the joke we like to call the 16-inch Pro a Turing-complete space heater. It's just a heater that happens to be a calculator as well. And it can run some compute if you're lucky. And the new M1s are just incredible in terms of single core performance and the amount of power they draw and how great they can be. The whole thing I was working on with that Minecraft bot and like recording and streaming and running Minecraft and running the bot at the same time, all of that was happening on the M1 while it wasn't even plugged into charge, and my battery lasted a good 5 or 6 hours, and that blew my mind. So that's where I do my local coding, but again, most of the actual like development of software in terms of like GPUs happens on the cloud. And while a lot of these machines, while I can't give like exact details on what's on these machines, a lot of them are GPU powered. My favorite machines, I will say personally, are the AMD EPYC machines. AMD's even beating Intel in the data center now. And there's some AMD EPYC machines with like hundreds of threads that are really fun to use, really fun to scale software on. I gotta say, something that takes multiple seconds can take a second on one of those machines. And then there's also machines with like GPUs and all kinds of really fun stuff. So it's an M1 locally, and then NVIDIA GPUs and AMD EPYC CPUs in the cloud.
Yeah, M1 is
Actually,
pretty
sorry,
powerful.
just really quickly, one of the most funny things I've ever done, two actually really funny things, is there was this one machine where I had like I think half a terabyte of RAM, so like 512 gigs of RAM, but I only had 100 gigs of storage space, and I was running out of space for my models, so I literally just made a RAM disk for 300 gigs and was like, let's just store everything here, and it ended up working very well.
You
um,
see,
this
the
other time,
secret, sorry, I just remind me
yeah.
that I just realized the secret to having an ultra fast computer is you give it an ARM CPU so that it's made to just, always be running and go to sleep. And then you get rid of your SSD and you just have a lot of RAM. And then suddenly it's like, this computer's incredible, but you can't turn it off. All right. That's the one rule we have. The CPU is designed to stay on as many hours, put it in sleep mode, whatever, just don't shut it off. And it'll be incredibly fast storage performance.
We should design something like that. Good idea. Anyway, this other time I was working on a large prime calculator, and Michael, you know all too well how much time I spent on that prime calculator, and I distributed it across 192 threads, and it uses bit arrays, and it ignores even numbers, and it uses wheels, super memory efficient. Still, to calculate the trillionth prime, it needed more than 512 gigabytes of RAM, so I had to allocate like another terabyte of hard drive space as swap to get it to even run. So yeah,
Only a
this is
terabyte
pretty intense.
laughs in M1. Moving on to the next question from Mystery King. Mystery King asks, why can't we create our own language?
You can. Um, so first of all, why can't we? Well, there's no reason you can't. You can. But I will say it's very difficult, and there's no reason to. Is what I would say. It's kind of like asking, why when we're born do we learn how to speak English when we could invent our own form of communication specifically to communicate with our parents? And you absolutely could. But why? Is the question. If you learn something like English, it's standardized. You can communicate with a few 100 million other people, and there's no ambiguity. There's no process of inventing your own language. There's no difficulty of that. You're just learning something that already exists. And then, since natural language is ever evolving, you can then take part in society and work on evolving it. Right? There's all kinds of new words and language that we use today that maybe we wouldn't a couple of years ago. And same thing with programming languages, right? If once you're part of the Swift community, you can contribute to the Swift evolution forum, and you can say, you know what, I really like the fact that Swift will automatically synthesize protocol conformances, but it doesn't work for classes when it's hashable. So let's make that happen, right? So you can do those things automatically, or rather you can contribute those things. Building a language is something that I've been interested in for a long time. Generally, the way you would go about doing it is by, of course, creating your whole sort of syntax parser, getting something to understand the syntax of your language, compiling it to something like LLVM or machine code, and then optimizing it. That is incredibly complex. People will dedicate their entire lives to figuring that process out. And even today, there are some simple pieces of code that you would think compilers would be able to optimize, but they can't. And at the same time, there are incredibly complex pieces of code that you'd wonder, how do they manage to optimize that? And they do. So, it's honestly, it's a lot more trouble than it's worth in a lot of the cases. If you do, however, have a great idea of, there's this one language feature that's lacking everywhere else, or there's this one platform that isn't well supported by any other language, or some certain toolkit, feel free. Honestly, go ahead, use something like LLVM, MLIR to get into the world of building your own languages, and who knows, maybe All right, we're back, everybody. Hopefully the stream is a lot more healthy now, and you can actually hear us.
We gave it the
Which,
Pfizer vaccine.
I'm looking forward to Johnson & Johnson, single shot. But I'll take what I can get, though. So, everybody should be able to hear us now. Again, let us know if there's any issues with the stream, and we'll go ahead and fix it. Once again, we got to figure out where the internet lives so we can get it to be better for us so soon. But go ahead, Michael. What were we talking about before we encountered internet issues?
I was talking about how Python's pretty old and how it took a long time for people to really start adopting it as a mainstream language. But I pretty much finished there. The next question that we have is from Mayank, who asked, and this is a rabbit hole, so it's going to be a fun one to see what you say to this one. How does a compiler work?
Oh boy, that's that's a question that a lot of people will ask, and there's a very long answer to it. But I'm going to summarize because brevity. So so essentially, if you look at what a compiler is supposed to do, it's actually conceptually quite simple. You have code that you've written in a high-level language. So for example, var I equals 0, I equals I plus 1, print I. That code to you seems simple, and for a human it is. But for a computer, that is hundreds of instructions, because those instructions are very low level. For example, when you set I to 0, what you need to do is take, for the sake of this example, let's just say there's no registers and no stack, just memory, right? You've got to take some place in memory, you've got to set it to 0, then when you do I equals I plus 1, you've got to load in that 0 from memory, you've got to add the number 1 to it, and then take whatever the result is and put it back in memory, and then for printing it, you've got to somehow call the operating system and be like, how do you print? And the operating system handles the printing for you. So what the compiler is supposed to do is take that high-level language and somehow translate it into the individual instructions that your CPU can actually understand. And lots of compilers, are very good at doing this sort of thing, but there's a lot of intermediary stages that go through. For example, when you write code, you are more than likely doing things the inefficient way because you're a human, and humans aren't very good at optimizing things. If we really sit down and look at the CPU instructions and try and figure things out, we can be pretty good at optimization, but a lot of the time, we're trying to code fast, not actually write fast code. we're trying to code fast, not write fast code. So what compilers will do is they'll take your high-level sort of code, convert it to machine instructions, but then they'll look at sort of common patterns of machine instructions and convert them to other patterns that are known to be faster. So for example, if you were to run a loop like for I in 3, print I, you would print 1, 2, 3 in Swift. And maybe what the compiler would do is instead of actually running a loop and checking if I is equal to 4 yet and then branching out, otherwise branching back in, instead it'll say, you know what, we know we only need to print I 3 times, so let's just hard code print 1, print 2, and print 3. Faster. Or sometimes maybe the compiler will recognize that, like for example, a long time ago when I was implementing some really weird mathematical logic, I wrote a function to rotate a point counterclockwise, but then to rotate it clockwise, I was like, you know what, I'm too lazy to write the clockwise function, I'll just call the counterclockwise function 3 times. So I made a loop and called it 3 times, honestly just to see what the compiler would do even. And what the compiler did is, and this is so fun, it took the loop, it unrolled it to 3 different function calls, then it took those 3 function calls and instead of actually calling the function, it inlined the function so it now had all the instructions there, and then it saw that the math was repetitive and just optimized it down to a single call to those mathematical functions. And the compiler was able to do this. The fact that it could is pretty incredible. So, I would just say that, the way compilers work is they take your high-level code, they try and understand what it does, they try and make it a little bit faster or a little bit better, and they try and convert it to individual instructions that your CPU or your computer can actually run. So, again, as you said, Michael, it's a huge rabbit hole that we could spend hours and hours digging into. You know that I've gone on huge rants about compilers before. But overall, that's what they're supposed to do. There's different kinds. There's ahead of time, just in time. There is interpreted languages. There's all kinds of things. But overall, that's what compilers do.
Yeah, pretty much. I don't have anything to add to that. That was pretty much the exact answer. It's a Very, very, very deep rabbit hole. That is always surprising how they're able to parse what you're saying and like use like sometimes because you know me, I'm a math guy, but sometimes I'll look at some of the optimizations they make and I'm like, how does the compiler know to how did
Decades of work is how.
yeah.
So yeah, like the C compilers like LLVM and like GCC, quite literally hundreds of thousands to millions of man hours have gone into identifying and optimizing structures of programs. The amount of just human ingenuity that has gone into that is absolutely incredible. Kind of funny, I was seeing a Reddit post the other day on the FreeBSD subreddit because that's one of the subreddits I follow. And the free, BSD is an incredible operating system, one of my favorites. And one of the things about BSD is that it's super lightweight. And someone was saying, why is a lightweight FreeBSD distribution taking up more space than like a Debian distribution? And it turns out that's because FreeBSD actually ships with LLVM pre-installed, and LLVM takes up like 60% of the space of the entire install. So the entire operating system, kernel, user space, utilities, everything, and then there's the compiler. So compilers are huge. So just they're pretty big, but don't let that discourage you from actually getting into it, because I'm gonna say nobody understands how entire compilers work, individually. Even I've seen like head compiler developers for like C++ and like Clang++ and these sorts of things will be like, that's a C++ language feature? I never knew that existed. Right? Like I've been
taught. Do that?
exactly. And you would think that the C++ lead compiler developer would know this, but they don't. Let's remember that not everybody knows everything. In fact, nobody knows everything, and it's really just a matter of experience and time for you to get into these sorts of things. So don't let me discourage you, but they are very huge pieces of software.
They start looking into it. They're like, wait, but what does that compile to? So our next question is from Sweeties Live, who asks, why do we need to be good at science subjects when we want to enter the fields of technology?
Again, ties right back into the fact that technology isn't its own thing. Technology is the backbone for pretty much every other industry. And every other industry, at least a lot of them at least, are powered by science, right? So maybe take a look at, I know Michael's your I don't know if it's voluntary or not, but you're in materials engineering. uh, so I'm not sure if you were voluntold or whatever, but you're in materials engineering, and like for example, in materials engineering, a lot of technology is applied, and that technology ranges from using tech to find new materials or to predict properties of certain materials that we can't actually physically make or whatever. I don't know if I got that right, so let me know if I get anything wrong there. But in order to apply technology there, you can't just be a programmer. You need to be a programmer that actually understands the materials well enough as well. Right? It goes back to what I was saying with machine learning experts needing to be domain experts as well. Like if you're implementing item recommendation for Amazon, it helps immensely if you not only know machine learning, but you also know retail and how products sell and the psychology of selling things and business, right? All of these things tie into each other. And so just the sheer fact that you implement technology in scientific fields and domains automatically sort of makes it so that science is incredibly useful. And that doesn't even count the fact that, qualitatively, science is a very problem-solving based thing, right? It's when you learn math, you're not really learning individual concepts, well you are, but you're also learning how to take those concepts and apply them in some sort of unstructured way, a way that you may not have done them before, in order to solve some kind of arbitrary problem. And doing that gives you a lot of experience on how to apply similar problem-solving techniques to machines as well. So I would say that, if your only goal is to sit around and solve random technical challenges, like how can different processes do inter-process communication as fast as possible, like if that's your only goal, sure, maybe you don't need that much scientific knowledge. But then if you want to implement inter-process communication in a large Cray supercomputer that's calculating the orbit of planets for NASA, you're probably going to want some science knowledge as well. So it's because of the application of technology, not necessarily in all cases the technology itself. But once again, exceptions to everything. Lots of things that are pure technology require some science knowledge too. So I think that's sort of the middle ground.
Yeah, and also just to be a little more direct with it. The thing is, technology is science. That's what it is, period. So even if you don't want to be, domain expert in something specific like materials, you still need to be good at science because that's what programming is. That's what computers are. I have taken courses on electricity and circuits and waves, and you have like, okay, here's your initial voltage and here's your battery here, and you have this junction there, calculate the amount of current passing through this point, and you have capacitors, you have all these different things that you go into when you have to learn circuitry. And that's important because if I wanted to be a computer engineer designing CPUs, I need to know, at the very bare minimum, the basics on how these circuits work. If I wanted to, these are the fundamentals of building computers. So when you have these new computers being released every year, you need to understand how that works. And even if you look at the field of material science, even if you throw programming out the window, if you just want to work at a tech company, let's say you want to work at Apple, they have a specific type of aluminum on their MacBooks. Why use that type of aluminum? I think I just hit my mic, sorry. Why use that type of aluminum? You can remember with the iPhone 6, they came up with this brand new design, right? This completely different, it was taller and wider and all these things, but people noticed that it would bend in your pockets, right? And the iPads were doing that too, right? It bends in your pockets. It's like, yeah, we use this new material, but we didn't have the material science, background looking into it correctly to say, by the way, this material is very malleable. That's a term we use for something that bends pretty easy. So it's very malleable. It bends really easily, and they didn't think of that. And now they have this new aluminum that they use in all the devices that's very, very, it's very stiff. It doesn't really move. And from a material science standpoint, you can go very deep into that. You can look at, it's not just aluminum. You don't just say, I'm going to make my MacBook made of aluminum. There's different kind of aluminums. There are different alloys. They say, okay, let's mix it with copper. And here are the properties that we get if we use this amount of iron versus that amount of steel and things like that. So there's anything you do, honestly, in the field of any form of technology is science. Science is the backbone for all of it.
And then getting even further into specialization, correct me if I'm wrong, but I think even within materials, specializing in metals is its own thing too, right? Like
metallurgy
and all these things, right? it's
a whole thing.
Exactly. It's not even just materials. Then within materials, there's also specializing in metals. It's so complex. And also, love Apple, but dear God, the Macs chip so easily. The aluminum on the Macs. You walk by someone with another Mac, and your Mac just suddenly is shaved from the outside. So, yeah, that's something Apple's got to figure out. Maybe they should hire you.
But yeah, there's just to add to that, there's a lot that goes into even when you have the specific type of aluminum for these MacBooks. You can actually, this is something really cool. There are sometimes you can take, let's say, a pure metal, and you can just apply an incredibly thin coating. We're talking atoms thick coating of some other composition, and suddenly your material is 10,000 times stronger. And it's absolutely incredible. So there's a lot of detail that goes into, hey, we're making a new computer screen. What do we make it out of, right? And that's the thing. And that we're only talking hardware here, right? So even when you get into software, it gets more specific, and it's a trade-off because even in the field of material science, where we're making these materials to put in our new computers, we're then using these computers to come back and help the field of material science. Because the funny thing about material science is it's built on chemistry. That's the fundamental science. If you talk physics, biology, and chemistry, it's all chemistry. And the funny thing about chemistry is we kind of don't really know what's going on. A lot of it is theory, and a lot of, you can argue a lot of any science is theory, but there are places in materials where we can say, this is what happens. We don't really know why. And it's kind of because we don't really know the chemistry behind it, because we're just not there yet. And that's how chemistry works. There's a lot of people in the field of chemistry, right? It's always been about, let's figure out why these things around us happen. And sometimes we kind of just don't get it.
Quantum computers have entered the chat here.
Yeah, quantum computers have entered the chat, right? So that's the physics version of these things we don't understand in chemistry. I remember when I was in first year, for any of you who are into science and you've done chemistry, you have to learn to draw molecules like benzene rings and all these things. But we haven't really been able to actually see them, because we know atoms are so small that you can't just look at a microscope and, oh, look, there's a benzene ring with one oxygen and whatever the case. But then, in the past 5 or so years, we've been able to develop these kind of microscopes that can see these orientations. And what we found is when we look at these, let's say glucose, for example, if we look at glucose through this microscope, we get the exact shape that we've been drawing for the past 100 years because we estimated these shapes using the way they react, the mathematics behind it, and all these other kind of things without actually seeing it.
Dear
And
God.
it's great to see that we're actually correct in some of these assumptions.
Humans are incredible.
Yeah, we really are. And it's kind of funny because in programming, you have the theory, you can develop the hardware and the software and then watch it go, versus in other fields in science, you kind of have the end result. And the question is, how did we get here, right? Because chemistry wasn't just like invented, like we woke up and suddenly we can make molecules. We've always been able to do it. So the question is, why does that work? How does the universe do that? And so that ability to be prompted with a question, with the end product and looking for the result, or looking for what results in that end product, and working in both ways, that idea of problem solving in that manner is very important, whether you're actually going to be working on a hardware level or a software level. And computers are just an example of science. Technology is just an example of science. So when you ask, why do you need to be good at science? It's because that's what you're doing. It's like saying, why do I need to be good at economics to be a really good, investor and stock trader? It's like, yeah, you could learn that stuff on your own, but someone who understands how this is all actually happening, you can look into a company's finances and understand their financial report, can probably make a better guess as to what the stock is going to look like in a couple of years for this company.
Precisely.
So yeah, very long so. There's my little rant that I get to go on. So Joe Met, I hope I'm pronouncing that correctly. John Official is the other part of the name. So John Official says, I have a question. How will you approach an innovative solution? What will you look in it? So what will you look for in an innovative solution? If you're finding it very useful, will you guide/support it? So I think this is referring back to the programming languages that we're talking about, like building your own programming language. So if you were to build your own language, how would you approach saying, like, oh, I have an innovative way of solving this programming problem with a new language? And how would you look into it? How would you support it, kind of thing?
I mean, the first thing you gotta see is what's an issue that we face today. And it doesn't necessarily need to be one that people are complaining about, right? Like before Swift existed, it's not like people were saying, oh my God, I hate Objective-C so much that I'm not even gonna make an iOS app, right? People weren't saying that. I mean, maybe I was, but a lot of people weren't saying that. Before Kotlin existed, actually, no, people were complaining about Java. But, there's all kinds of, issues that we face. Some that, maybe we realize, some that we don't. And what you need to do is you have to start off by saying, what's a problem that people face, and do I have the technical capability to solve it? It's actually pretty similar to any other kind of business or thing you invent and sell. Is quite literally, is this a problem that people need solved, and does my solution actually solve it well? Does using my solution generally add enough value to people's lives to make it so that it's worth the time and effort to use my solution versus what they would have done otherwise? Is my path actually less friction than the other one? So for example, one of the things that I've noticed is that Swift, for example, has incredibly elegant syntax and a wonderful optimizer. Rust, however, has great memory management, but its syntax is a bit questionable. And it has an absolutely state-of-the-art compiler stack. C, we all know C. It's unsafe, it's old. It works though. C++ is like C, but you slapped on classes and were too unwilling to change anything about C. And then you've got Java, which is, if you many years ago, what was it, 26 years ago, you had, access to languages like C++ or maybe the very, very early versions of Python, and you just had to build something that worked across platforms, which was high level, but also simultaneously low level enough to not really have a good standard library. So there's all these sorts of, issues with all these languages. So what if you could somehow take all the great parts of those languages and make one language? Now, of course, you can't really do that, because if you could, that would already exist. But you can cherry pick, right? So you can say, we can take the Rust optimizer and memory management with Swift-style syntax, with support for Go-style Go routines, with support for Kotlin-style multi-architecture, so you can go to JVM or ahead-of-time compilation. And you can say, all right, how is this all going to fit together? What's the compiler technical stack going to be? Is it going to compile through LLVM? Am I going to have my own intermediate representations? If so, will it be powered by MLIR? And then from there, you ask yourself, what does the syntax look like? What's the process for people to contribute to this language? Right? What's my evolution going to be like? How's the community going to be structured? And then once you figure that all out, then you actually start building. Is what I think. You can start off with something simple. Like, for example, a lot of languages that I know of actually started off as like very simple implementations of slow compilers that just kind of worked enough to show off the syntax of the language, literally an MVP of the product. So for example, Go in the beginning was implemented as a GCC front end. So it wasn't even its own compiler, it was just a new front end for the GCC stack. And then eventually they transitioned to using that to bootstrap their own Go compiler built in Go. And so, there's all kinds of ways you can go from there. But overall, identifying the innovative idea comes back to pretty much innovation principles, which I know Michael can talk a lot about, which is, identifying the sort of problem that programmers face and seeing if your solution is less friction than what they would have already done to solve that problem today. And if it is, great, make the language, see if people adopt it, and if they do, work towards evolving it and sort of continuously meeting new needs. Because again, technology evolves. So do programming languages, right? If there's a new language feature, not a new language feature, but rather a new operating system feature, you're going to need your language to support that. So it's consistent movement and updating and supporting new paradigms and architectures. So overall, it's pretty similar to identifying any kind of innovative idea and then supporting it through the whole process of building out an MVP, getting people's feedback, and working towards architecting more and more complex versions of it.
Yeah, absolutely. So I think we may have been having a little bit of network issues during that response, but I'm checking the stream now and it seems fine. So I think we're able to just keep going.
All right.
As someone had mentioned about material science again, so I wanted to just jump in very quickly and add that I did a little bit of searching while you were talking, and the specific aluminum that Apple uses on their unibody MacBooks is called aluminum 6061, which is part of the aluminum 6000 series. And that's so this is where like material science becomes useful, because I can say from the 6000 series of aluminum, that means its biggest composite is magnesium and copper. And I'm thinking of this because someone had asked about, like they said, apparently Apple uses more than half the elements in the periodic table. Yeah, Shiva said, I heard Apple uses more than half the elements in the periodic table. The specific aluminum they use can use up to 6 other metals as a percentage of the actual end result. And aluminum is just the remainder. So for example, you have chromium up to 35.35%. And that's incredibly small, but that just shows you how like material science is so specific. Chromium up to maximum 35%. Yep.
So I guess you could say it's a Chromebook.
All right, and that's the end of our street now. So it's like chromium, for example, maximum 0.35%, maximum 0.4% copper, 0.7% iron, 1.2% magnesium, 0.8% silicon. Like it's incredibly small amounts of these other materials, but they come together to make, which as easily as they scratch, I honestly believe these unibody MacBooks are very sturdy. And I've never really picked one up and just bent it or anything like that. So I think it's a really good design for them. And then with material science, you can start looking into what is its thermal capacity. I know we talked before a little bit about M1, and now I had the 16-inch MacBook Pro with the i9. I know those fans were spinning, and sometimes I would just be sitting on my bed, laptop in my lap, and my legs were getting warm. And you can think about, like, for example, if I'm designing the new Mac and I'm noticing that there's a thermal issue, I might think, okay, well, maybe the aluminum we're using might not be the best because the amount of heat that it's able to transfer onto the actual exterior is relatively high. And these are the things you can look at with material science. And you can even say, well, the CPU gets 90 degrees, but our specific material at 30 degrees becomes a liquid. So that won't be any good. It's a whole thing, and maybe they do use more than half the periodic table. I would guess I'd have to look into every one of their products and what they are combined with. But it could be very well plausible, because definitely when you say something like, oh, this is made out of steel. Well, what is steel? It's mainly iron and carbon, but you can throw in a thousand other different things in there, and you get different kinds of steel, right? So you have stainless steel, you have whatever the case. So it's a whole world on its own, and that's an example of understanding science to get a better understanding of technology, because someone at Apple has to think of that stuff, right? When you test these computers and see this is how hot we'll let it get, someone at Apple has to say, okay, what are we going to make these things out of so that we don't have any issues? You don't want the laptop melting when it gets too hot, right?
Or at the same time, not so thermally conductive that you're burning the person's lap off, which
Yeah.
arguably the i9s do, but still,
Kind of, yeah.
there's some kind of regulation around that. So yeah, that's definitely very much needed within the world of tech. Is you would think Apple, it's a tech company, they write software, they make hardware. Why would you need a material specialist? But they really do. In fact, much more than you might think they do. And same thing with IBM. You would think, it was, again, going back to one of the things we mentioned in a previous episode, you would think they're a tech company. Why would they need content writers and people who can make social media posts? It's because they still do marketing. They still do write documentation for developers. They still do outreach, right? Even though they're a tech company, they have all kinds of different facets. So it's, companies require a lot more than maybe what meets the eye.
Yeah, absolutely. Everything
also
requires so little details. Yeah.
I gotta say, really, unfortunately, YouTube is being very uncooperative right now, and I do not know why, but it is not allowing us to maintain smooth streaming. So you will experience a little bit of buffering. Hopefully, you can bear with us. The replay should be a lot better than this, though. So again, thank you for bearing with us during the weirdness that YouTube is putting us through. But really quickly, interesting bug in YouTube, adding just yet again to their instability. It gave me a little warning just now, saying that the stream's current bitrate, here's the number, 7,300 kilobits per second, right, is lower than the recommended bitrate of 4,500. I don't know if my math is off, but I think 7,300 is greater than 4,500. So the stream should be fine.
Carry the one.
The stream should be fine, but unfortunately YouTube is being a little weird. So again, thank you for bearing with us. And again, if there's anything you miss, hopefully you can either scroll back a little bit or the replay should be a lot better. But yes, more.
This is where we jump in. We've identified the problem. Now we need to make a new YouTube that doesn't have this issue.
And we'll call it Vimeo.
Called it LinkedIn. No, that reminds me of if any of you have ever watched The Sweet Life of Zach and Cody as a kid.
Oh God,
there's this one. Yeah. So there's this one. He was like, I don't want to. He wasn't like the plumber. He's like the maintenance guy. I don't really know the term. He's kind of just like maintenance of the entire hotel. And there's this one episode. I think it's like they live in an alternate reality where the kids were never born or something like that. And he comes in with this skateboard and he's like, "This is my incredible new invention. I call it the television." And the kid's like, why do you call it the television? He's like, because I had the vision about it and I just needed to tell somebody. So we'll make a new YouTube platform. We'll call it LinkedIn.
Might get sued for that.
Yep. Our next question is a bit of an older one, but we'll ask it now. It's from Sabita, who says, "Hey Tanmay, what are the programming languages you have learned until now?" So let's do a count. How many languages? Let's say languages that if someone gave you an application to make that required this language, you'd be able to do it, no matter how simple or complex. Just if said, "Hey, we need you to do this quick thing in this language," without having to Google and learn the syntax, that kind of thing, just off of your head, understanding of the language. What are the languages that you could use?
So completely off of my head, to the point where I can just like synthesize new forms of syntax that people haven't come up with before. Things like Swift. You may remember a little while ago I came up with this really weird concoction of syntax where it was like optional variable, question mark, fatal error, and that would forcefully unwrap. And that was something that I checked. No one had ever done that before, but I was able to guess that would work based off of the way the compiler works and the way that the syntax parsers structures like fatal errors and things. And I was able to figure it out. So I would say that the main languages where I can just sort of go, no need to Google whatsoever, would be Swift and Python mainly. Then ones where I can code very efficiently, thoroughly, I know how they work, but occasionally I might need to Google like the standard library or something, would be like Java, Go, Kotlin, C, C++. Actually, C would also be in the whole like Swift family, actually. But yeah, C++, I might need to Google a few things occasionally, and JavaScript. And then there's the languages that I've coded in before, but that I don't, or actually, no, Julia would also be part of that banner. So Julia, so Go, sorry, no, Go and Swift are Go, Swift, and C are the ones that I really know, and then there's Java, JavaScript, Julia, all the J's, Kotlin, and C++. But then, of course, there's the ones that I've coded in before, but don't really have all that much experience with. So things like HTML, CSS, which not really programming languages, but close enough. And then there's
an angry mob of web developers rise.
There's things like, I guess TypeScript technically is JavaScript. I don't know if web developers are gonna hate me for saying that, but I guess technically TypeScript is just compiled to JavaScript. So okay, I've used it before, but I don't have much experience with it. I'll count it separately. And then there is one more that I remember, but unfortunately it's skipping my mind right now, which is incredible. Rust. So I have used it before, but I don't have enough experience with it to just be like, give me an app and I can code it. So, but honestly, any of these languages, it's really just understanding programming concepts that matters, not really individual languages. Of course, it's great to be able to specialize in one. Like, for example, Swift, I know well enough to just, off the back of my hand, you show me like a Vim file with Swift code and I'll tell you if it'll compile, right? But then maybe I couldn't necessarily do that for Java, but I could still write in Vim without needing syntax completion, right? But then again, any other language that I want to learn, it's really a matter of, hey, I want to do a for loop. How do I do that in this language? Right? It's relatively simple. So even though I don't think that's necessarily a good measure of how much a person knows is their programming languages, those are the ones that I'm most familiar with.
Yeah, and funny enough, even when I am learning a new language, I don't like using like autocompletes in like I still use Vim just because it's the weirdest thing in the world. I find it gets in the way because as I'm typing, I can't see what I'm typing because it keeps putting up a window right beside my cursor. Like, here are all the things you might type next. It's like, let me type it, please. It actually blocks
I equals 0. I equals. You haven't used I anywhere.
Relax.
They're too efficient. And then sometimes they're just slow. Like, as I was coding this Minecraft thing, I had to go out of my way to find a workflow that didn't need IntelliJ, because IntelliJ is just getting in the way. It's hindering my typing speed because it can't update the screen fast enough, as fast as I'm typing at least. And whenever I compile, it gets so slow to the point where I can't even use the IDE as it compiles. I don't know if it's an Azul JDK bug or an IntelliJ bug or whatever, but it's just slows down to a snail's pace. So really, honestly, it's Vim is a great way to code once you get used to it. I used to swear by Nano, and I'm ashamed of myself for saying that. But I used to back in like 2018. But one of my mentors, actually Steve Martinelli, who was on the show a little while ago, him and a couple of the folks that work with him, got me introduced to the world of Vim, and ever since I have been a child of using Vim.
Our next question is from Hamad, who asks, how much does knowing how compilers work help in making you a better programmer? I want to answer with the baby version, and then you can go into the super complex because you know everything programming lord kind of version. So I was doing a leak code problem, and I'm pretty sure Tanmay knows this one. I was doing a leak code problem, and it was a very simple question. It was like, we want you to take the 2's complement of a number and return the base 10 version, basically. So what you had to do was like convert it to binary, flip all the 1s and the 0s of the binary version, and then return it to a base 10 number. And Tammy and I get into the practice of trying to one-line as much code as possible just for the sake of it, never for production, but just, hey, can you one-line this? So I did this one-line code. So Python has this built-in function called bin, which if you pass it a number like bin of 3, it'll come back and give you the binary of 3. And so in my one-line solution, I had called this built-in method 3 times. I did bin of n and I compared it. I did bin of n again and bin of n again. And I was sitting there, and when I submitted the solution, it was like, okay, you're faster than 50% of submissions. And when I looked at the solution, I was saying, hey, well, Python's interpreted. It doesn't really have these compiler optimizations that you and I talk about sometimes. So I'm thinking that every time I call bin n, n being the number I was dealing with, Python is going to actually go to the back end and run through that every single time, versus a compiled language might catch that and just do it once and just paste it, sort of like paste the results every time I use bin of n. And so what I did was, instead of making this a one-line solution, I made it 2 lines. And the first line was I called bin of n and saved it in a variable. And then I used that variable in that second line instead of calling bin of n 3 times, because I said, referencing the value, like going to a variable and getting its value has to be quicker than calling this method. And then suddenly I was faster than 93% of people when it came to Python, because I was understanding, okay, well, a compiler would normally come in and make this specific optimization to make it faster, but Python isn't going to do that. So my understanding of how a compiler might work in this situation allowed me to say, here's what's not being done in Python. So here's how I can make it faster.
Precisely. I love that example. There have been so many times where I will open up this wonderful app known as the Godbolt Compiler Explorer. Check it out if you haven't already. And I'll be like, what, my code isn't fast enough. I wonder how I can make it faster. And I'll write like a C version of it and then go in the Godbolt Compiler Explorer and just see what the compiler ends up compiling it to in assembly, and understanding that logic and being like, oh, that's a much better way of doing it. And then just go back to like Python or wherever I'm doing it and implement it that way. So there have been so many times where I'll do that. And really all I can say is, when you understand how a compiler works, you understand how the language works at a fundamental level a lot better, and that can help you make decisions as to what constructs to and what not to use, right? Like, for example, within Swift, maybe you know that using the guard else instead of an if and return actually is a little bit faster, because it makes a bit of an optimization in how like arc is handled. Random example, I'm not sure if that's an actual optimization that they do, but let's just say for the sake of it, guard else has this is some sort of like tail call optimization or whatever in recursive functions. And that, and so you can be like, okay, I can make my code faster because now I can use a guard instead of an if. Or maybe you understand that Swift arrays are passed by value, and so what you want to do is get a pointer to the array. Otherwise, Swift thinks you're going to do a write even though you're not doing a write, and then it calls the copy on write, and then it makes a copy. You can understand these things, which I don't think you can understand purely staying high level at a language. Even in Python, a high level language, if you understand it at the low level, as as Michael said, it can really help you as you write code. The other day, Michael was working on this really interesting problem around finding the largest palindrome product, which you've yet to figure out. But
it works. It's just not fast enough.
Exactly. So he implemented a function to check if a number is a palindrome, and I implemented a Swift version which was super fast, and it basically used a bunch of divisions and mods and multiplications to reverse the number and check if the two integers are the same, no strings involved. And I was like, just do that, it's way faster. But the way he was doing it in Python was reversing a string and checking if the string is equal to the string of the number. And you would think that strings would be slower, because then you've got to create a pointer, you've got to have memory, you've got to allocate it, you've got to free it, you've got to garbage collect it, you've got to do all these things. But in Python, his solution was faster because Python's not compiling it to be fast enough. And so the string reversal logic, which is actually written in C internally, ends up being faster than the integer logic. Wow.
Yeah, and because I remember, so like the original version, because I hadn't touched this code in a few weeks. So the original version, we had tested it. You were supposed to return the largest palindrome when you ran through numbers 1 to 8. And so when we tried 1 to 6, it would work fine. But then in 7, it just seemed like it was never going to, it seemed like it would literally take forever. I have never actually seen the result for 7. And my original logic for checking if something was a palindrome was, dividing by 10, temporary values and all these other divisions and modulo kind of thing. And then when I switched it to just take the number you pass the function, convert it to a string, and then just return that string equal to the reverse of that string. And then, Tanmay's looking at it like, oh, but that's so much slower, strings and exactly everything he was saying now. But then suddenly it could do 7 in 40 seconds versus we were waiting 10 minutes and we never got a result. So
I think the
it's definitely
30,000 hours, like 4 years to compute. God, no.
And so like exactly as Tanmay said, because he was looking at it, it's like, maybe because it's built in, the library is built in C. And so having that understanding of how languages work on the back end, how they're being compiled, or what happens when you hit run, gives you a better understanding of how your code is interpreted and how you can use that to your advantage. Because again, and I remember when I was getting into the world of compilers and learning how they work, one of the things Tanmay was telling me is like, don't try to optimize certain logic because the compiler will optimize it way better than you ever could. And that's true, right? It's exactly as I was saying before, millions of man hours have gone into making these compilers. And they are able to take certain problems and understand it to the simple, because like you might come across a problem and you might think of the first mathematical solution that comes to your head. Meanwhile, some compiler developer has spent 5 years working on how to compile this exact problem into the most, the simplest way possible, the lightest weight solution that exists.
3 quotes in computer science that I absolutely love. First of all, premature optimization is the root of all evil. Never optimize your code until you profile it and you know what the hotspots are. Okay? Number 2, there are only 2 hard things in computer science: naming things, cache invalidation, and off by 1 errors. Yeah. And what were we just talking about? There was one more that was related to what we were talking about that unfortunately I was just skipped my mind here. We were talking about like the Python. What was it?
I started with like the Python with the bin function and saving a
Yeah.
variable. Then we talked about how
Yes.
I turn it into a string.
And never try to outsmart your compiler.
Yeah.
Because in the vast majority of cases, the compiler knows way better than you. And that's why, in a lot of cases, writing assembly is way slower than writing C. Because the C is being compiled through a program that people have spent millions of hours getting to be as fast as they possibly can. So even if your code is general purpose, just the sheer fact that 40 years of effort from the open source community went into developing that compiler completely shreds your handwritten assembly code. At least in the vast majority of architectures and cases. Then again, there could be some sort of very, very use case specific optimizations that only you can implement or that you know can exist. So keep that in mind, but overall, knowing how the compiler works can be very helpful.
Absolutely. Let's see. So someone said YouTube. Yeah, the YouTube admins are reducing your speed. They don't want to see all the answers we're giving out here. So how much knowledge is a compiler? So we answered that one. This one is for Tanmay, so I guess I can't answer this one. This is going to be fun. Why is IBM using gold to build a quantum computer?
Actually, no, I feel like this one is kind of your thing. It's materials. But overall, I will say, however much very, very limited knowledge I have in materials, gold isn't a very reactive material. If I remember correctly. And I feel like that has properties that would be useful in quantum computers. I don't know how exactly they work internally, but I have a feeling that would be useful in quantum computers because you want as little interference in terms of like with materials and just general electricity and energy around qubits because they're very fragile. Like qubits, the fact that we can even make qubits like electronically is just mind-boggling. Like the fact that we can even do that. And when you put them in superposition and when you sort of manipulate them in certain ways, they only last in that state for a couple of microseconds at best if you're lucky. And so making sure that things happen very fast and things do not react with them, I assume would be very, very important. That's why they keep them at temperatures colder than outer space. And so I feel like that would be the reason. But again, I feel like you would need to ask someone on the actual IBM Q team, so hopefully we can get someone from the actual quantum research team on to answer that question in the future. But Michael, anything else to add that you guess might be helpful for quantum computers to use gold?
Yeah, absolutely. So the material that they're using, they're looking at this new material basically that uses gold. And what they're trying to, so first of all, in MIT, they predicted that heterostructures made of gold can become what we call a topological semiconductor under strict conditions. A lot of big words there. A heterostructure, a heterostructure is really like a material that uses heterojunction, and heterojunction is an interface where 2 layers or 2 regions of different semiconductors are interacting with each other. Specifically, when the 2 semiconducting materials have different unequal band gaps, or a band gap refers to the minimum amount of energy needed to excite an electron for it to participate in conduction. So what does that come down to? You're looking at two semiconducting materials where the minimum energy needed for it to conduct are very different. And what you're trying to do is create an interface between these two different materials, and that'll give you a lot of, several different physical properties that would be, I assume, would be useful for a quantum computer. The specifics I don't really know, but I could look into them. And there are many challenges that needed to be addressed before we could get there. But maybe we're in the area, because they did talk about this, like, I don't know, 9 years ago or something like that. So maybe now we're in the area where we're starting to actually play around with them. But gold, absolutely, it's definitely, it's not just pure gold. We're not just taking pure gold and shove it into quantum computers. We realize that gold could be very useful because there are specific properties that we want in quantum computers. For example, magnetism, electron spin, and all these other things. And we know that they can exist really well inside of gold. So we need to use gold to do this, but it's not as simple as let's just grab all the gold in the world and shove it in a computer. We need to create gold that has specific electrical properties for us to actually have a computer in the first place.
So for example, it's not just because they want it to look nice.
Yeah, that's just for style points. But for example, superconductivity and magnetism normally don't exist in the same material. You can't just have one material that's both superconductive and magnetic, but you want both when you're dealing with a quantum computer. So they have to make a material that uses gold, because we know gold is really good for it. They have to make a material that can do that. We can't just say, okay, let's grab our silicon and like the same silicon we use in our Intel CPUs. It doesn't work because, again, especially fundamentally it's different. Definitely. So speaking on so we have Hamad who says, speaking of quantum computers, I believe it would have very different compilers. So let's talk about compilers in quantum computers.
Ooh, my favorite topic so far. I love quantum computers, I love compilers, but you know what I love more than that? Both of them together.
Knowledge. Oh, okay.
So what I like about quantum computers is that because they're in their infancy, we have an opportunity today. We have an opportunity to architect the software stack around them in a way where it's ready for the future. When we made compilers for regular computers, 40 years ago with the GCC compiler stack, for example, we didn't really think about the future all that much. We were just like, you know what, let's just throw together a C compiler for the GNU suite. And I'm not saying that it wasn't hard work. These engineers did incredible jobs. But still, today GCC doesn't scale as well because it's not modular. It's a monolithic compiler. Similarly, if you look, BSD was from the very beginning designed to work far, far in the future, right? That's why macOS is based off of BSD and not something like Linux or its own kernel. It's based off of BSD and Mach because they're microkernels. They fit the certain design objectives that Apple has for their operating system, and it fits them very, very well, and it's going to work for the next couple of decades at the least. They literally made a processor architecture transition, and they're using the exact same technical stack. Then, of course, you have Windows, and they're just kind of chilling on DOS, and that sort of introduces problems today, because now when Microsoft is like, we want to transition to ARM, they're like, okay, we need to still maintain backwards compatibilities with applications all the way to like Windows 95. And how are you going to do that on a brand new ARM CPU that needs to be fast, right? You can't do that. That's why I absolutely loved Apple's decision a couple of years ago to say, you know what? No more 32-bit apps on macOS in the first place. Because you've got to rip off the Band-Aid hard and have developers and companies adapt, otherwise they won't. They're going to keep running the same apps from macOS Lion on macOS Mojave, or whatever sorry, we're not on Mojave right now, God. Big Sur.
Big Sur.
Why did I think of Mojave? Big Sur. But yeah, they're going to keep doing that. You have to force people to adapt. And similarly with quantum computers today, I think IBM in particular is doing an amazing job with their stack. And I say that, generally if you were to look at the industry, IBM has, first of all, the first like completely open source, just generally available quantum compiler that you can use and actually optimize quantum circuits with. It's still in its infancy. It doesn't optimize nearly as well as it can or should, but remember that optimizing for quantum computers is in and of itself also a lot more of a difficult task, because quantum computers have certain topologies, right? So only certain qubits can connect with other qubits in certain ways. And so optimizing a quantum circuit is almost like solving the traveling salesman problem, except we need quantum computers to solve it. So it's like, what came first? So it's very much still in its infancy, but we have the opportunity today to build better compilers than we've ever built before in order to make it so that we have this wonderful software and technical stack for the future when quantum computers are actually a thing. Right now, they're mostly a research thing, but in the future, they're going to be very widespread as accelerators for regular computers, and I can't wait until that day.
Absolutely fantastic. We have another question from Swarnadeep, who asks, what are the languages that you would suggest an 8th grader to learn?
Ooh, okay. Well, that's a hard question to answer because I think it really depends. It's not something that I can just answer, off the top of my head here. Specifically
the stream's
because,
frozen.
sorry,
Stream's frozen.
Oh, wait.
It's kind of.
Can you still hear me?
I can hear you on Zoom, but I mean like the
Oh,
actual
like
stream
on
itself.
YouTube?
Yeah.
Ooh, that's unfortunate. All right.
It's
Title card. All right, we are back. Hopefully, the tech should be smoother this time.
still frozen on my end,
Still,
unfortunately.
ooh, that's unfortunate. But again, it should be better in the actual replay. Hopefully. Then again, though, we are running towards the end of our session today anyway, so hopefully YouTube supports us for a couple more minutes here, and we can answer like one or two more questions, and then finally we will end today's AskTanmay, only to be followed up by another AskTanmay very soon.
Alrighty, so let's go with our last question here. Let me just make sure there aren't any I skipped, but okay, I think we're good. The last question we have today is from Mystery King, who asks, what is quantum supremacy?
Amazing question, and the reason I say that is because there has been so much hype about that. Google in particular, I think, is the main culprit for that. They kind of wanted some attention to their quantum computing stack, and so one of the things they did is they talked about one of their new applications which achieved what is called in the industry known as quantum supremacy. And the idea is that today there is no quantum computer that can do a task that would be entirely infeasible on classical computers. And generally, the sort of accepted number is after we reach, I think it's 32 qubits in actual quantum computers, is when we can start to achieve quantum supremacy. But that's just a theoretical number. That's not like a necessary, you need to reach 32 qubits to achieve supremacy. So the idea is, show a quantum computer actually calculating something that you could not have calculated without a quantum computer. Then we've achieved quantum supremacy. And the thing about quantum supremacy is that we haven't really achieved it yet. Google kinda sorta did with one of their applications, which they kind of marketed as quantum supremacy. But it really was something that IBM was then able to go ahead and recalculate on one of their supercomputers without needing a quantum computer at all.
Yeah, in like a couple of days.
Yeah, literally. Like I think it actually took less time than the quantum computer because the quantum computer was actually so like iffy and needed to do so many recalculations because of like errors in the
Yeah.
calculation. So I would say that it's something we haven't achieved yet. The concept is pretty simple. You know, now we have new kinds of computers that can do things that our old computers couldn't, but still, we haven't really achieved it yet. So hopefully in the future we will.
Yeah. So yeah, quantum supremacy, just the basic idea that, a quantum computer can do something that, as Tanmay said, is just not realistic on a classical computer. Google tried it, didn't work out too well. Must have been comparing it to like an Intel computer. I don't know. It's interesting actually, because the amount of time, it's almost paradoxical, because development in quantum computers right now is kind of slow. Like, it's fast in the sense that there's always something new coming out because it's a brand new field, but things that are coming out that you can actually just apply today are coming out very slowly. Mm-hmm. And the thing about that is, as time goes on and we're developing quantum computers, we haven't stopped developing classical computers. And so that band that you need to, that bridge you need to gap, and the gap you need to bridge, and how much further you have to go is also slowly increasing with all the time that we spend every year in which we don't reach quantum supremacy. So it's kind of, hopefully we're developing quantum computers fast enough that we can just eventually get there. And obviously, of course, eventually we will get there, because people talk about like Moore's law coming to an end in some time, however many time. I don't know, people say, 7 nanometers is it, and we get 5. And now TSMC is like, yeah, we have 2 nanometers, by the way. So I don't know when Moore's law comes to an end, but we do know eventually we'll have to stop. And maybe that's where quantum computers can take their rise. But it's interesting. I don't think it, especially because, Moore's law is still pretty much active. I don't think we can achieve quantum supremacy until that comes to an end, because the amount of power that the quantum computer needs to beat is doubling every 2 years.
Well, actually, you're right. But there is one thing to keep in mind, that regardless of the doubling of computational power, there's some problems that are just so infeasible to begin to compute with regular computers that regardless if Moore's law went on for the next couple of decades, we still wouldn't have enough compute power, right? Like, for example,
Absolutely.
brute forcing like AES encryption keys. That is designed to make it so that with hundreds of times more compute power than we have today in the far, far future, it still would be uncrackable. But the theory is that using Shor's algorithm on a quantum computer, a couple minutes, you're good to go.
Right.
So well, that's a bit of a dramatization of quantum computers, but that's the general gist of it. So I guess in a way, for most tasks, yeah, you would need to wait until Moore's law is slow enough to the point where quantum computers actually are worth using, but also at the same, for at least things like machine learning. But then at the same time, there are some tasks that are just completely impossible to run on regular computers, like simulating the activity of molecules and traveling salesman problem and Shor's algorithm and things that need to be run on quantum computers specifically. So
yeah, and it's funny too, because it's when you compare AMD to NVIDIA GPUs and you're deciding which one to get. From a gamer's perspective, for a few years now, it's always been like, yeah, AMD is good, but NVIDIA has ray tracing. And it's kind of funny, because to me, like, machine learning is like that ray tracing trick up the sleeve that quantum or that classical computers have that quantum doesn't, at least for the time being. Because, for example, if you look at even ray tracing itself, Jensen goes on stage back in 2018 and he's like, oh yeah, ray tracing won't be here for another 10 years, but we just use machine learning to make it happen now. And obviously maybe with encryption, you can't use machine learning to crack the SHA-256, but you can definitely use machine learning to solve a lot of problems that without machine learning, a computer would just take way too long to compute. And
the
especially
Go game is a great example, right? Go is just, the scale of it is mind-boggling. But then you just apply machine learning to it, and suddenly the program is playing against itself billions of games in like a week, and has gained more knowledge in the game of Go than every human who has ever played Go in the entire history since Go was invented combined, right? And in like 5 days, it's just completely obliterated every human.
So the question then becomes, like, for example, if we stay on the topic of ray tracing and we say, here is a scene that's designed and all the lighting and all this stuff is calculated with ray tracing. Now, a classical computer, it would take this 1,000 years to render this complex scene. But with machine learning and tensor cores and all these other things, it might take, let's say, 100 days or 1,000 days. Let's just keep the number 1,000. So with 1,000 years on a regular classical computer, throw in some machine learning and you get it down to 1,000 days. But a quantum computer can do this in 1,000 hours with no machine learning, whatever the case. Is this quantum supremacy? Because technically a classical computer can't do it, but we're using models to aid that, right? So it's the trick that it has up the sleeve. Is like, it's like Good we point. Say with AI upscaling. Another technology NVIDIA has is, why do I forget the name of things when I need to know? Their ability, yes, DLSS, deep learning super sampling, right? So you say, for example, when you get these review cards, AMD releases their new 6,000 series card, NVIDIA releases new 3,000 card, and they say, AMD is like, oh, look, this is a great 4K performing card. We're better than the 3080 at 4K games. But then you get a 3080 and you're like, oh, but this thing has DLSS and this game supports DLSS. So I'm using machine learning to get 4K with a much better frame rate versus the AMD GPU, which is doing it natively. So it's like, is that really a fair comparison to make? Yeah. And realistically, the end user, if they're going to see DLSS, they're going to turn it on. So unfortunately for AMD, when they say we are better at 4K than NVIDIA, they have to compare to NVIDIA with DLSS, even though it's cheating. Yeah. And that's literally the term I use. I say NVIDIA is cheating with this technology. And it's not really fair to AMD, but that's the competition, and it's a great technology, to be honest. So that's the thing too, is we're focused on building quantum computers, but there's two aspects of it. The first aspect is with every year that we're not, reaching quantum supremacy, it's technically going to get a little bit more difficult to do so. But also, with all the time that passes of us not reaching quantum supremacy, we're building new technologies on classical computers such that we don't need quantum supremacy. Yeah. Obviously, machine learning isn't going to solve every problem in the world, and eventually there are going to be problems that we just need quantum computing for. But until then, there is a blanket of problems that we can solve just by using more efficient methods and using models and all these other things that we just haven't done yet, whether the classical technology wasn't there yet, maybe the model hasn't been thought of yet, whatever the case may be. There are a blanket of problems that we can just solve if we were forced to stick with classical computers.
Mm-hmm. Right. It's a very novel thought, something I hadn't thought about yet. So thank you for bringing that up. See, this is why we bring Michael on the show to host, everybody.
This is where the innovation mindset sort of comes in. Absolutely. These are the things.
Symbiotic.
Yeah. That's as many buzzwords as we can. Did we mention blockchain yet? Yeah, the blockchain on the quantum. No. So it's definitely, and that's when I talk about innovation, and when I say I study innovation, even though generally when you think of innovation, you're thinking in the field of business. I like to say I personally believe I have an eye for innovation, and that's because you have to look at the system as a whole, and you have to catch these patterns. Like what I'm saying with using machine learning too. And I talk about this, Tammy, I talk about these kind of patterns all the time, like how AMD is combining their CPU and GPU power. And you have this, the technology that you get that only happen when you have CPU and GPU from AMD, and why that's so important for AMD specifically to have. And it doesn't matter if NVIDIA does it, or it doesn't matter if Intel does it, kind of thing. So, and I like to think it helps me get a better understanding of technology, is having an understanding of why people are doing it, where it's coming from, that sort of thing. But someone asked, can we reach PM semiconductor fabrication someday? I'm not sure. I'm really bad with abbreviations. I'm not sure what PM semiconductor fabrication is.
Neither do I.
I hear PM, I think product manager, unfortunately. Can we have a product manager that is a semiconductor? No. The thing about, PM the unit. Sorry, PM the unit.
PM unit.
Yeah, exactly. So I'm going to say no. And the reason I say that is the same reason that we thought originally 2 and 5 nanometer semiconductors wouldn't be possible. And while, of course, now people are saying, okay, we have them now, there are absolute limits in science. And this is one of them. And it's the same reason of you have quantum tunneling. Things don't work like what the thing about quantum specifically, and why quantum computers are so important, is people talk about superposition and all these other kind of things. But the fundamental idea is the smaller you go, the weirder things are. And it's literally that simple. The smaller you go, the weirder things get. And the more problems arise, when you try to do things that work regularly on a big scale. For example, we know through, I believe it's Bernoulli's equation, that says that anything traveling in space can be treated as a wave in space, right? So we already talked about electrons or waves and blah, blah, blah. But you can mathematically calculate what is the wavelength of something as big as Jupiter traveling through space if Jupiter was a wavelength instead of this big gas giant, right? You can mathematically find a wavelength that treats the universe the exact same way as this giant ball of gas does. And something as big as Jupiter can be a wave. Then something, incredibly small, like we're talking, picometers, these things definitely, they have these wave properties and they're able to have these weird traits. So that's really what it comes down to, is the science just gets weirder, right? In physics, there's two sides to it. There's the really small and the really big, and they're both completely different. As you start to transition, the rules of the really big no longer apply to the really small and vice versa.
God, the thing as a programmer, the thing that annoys me about that the most is like the thought of where does that transition happen exactly? Where it's like, yes, now we're being governed by new laws. It's like, it's kind of, I got to say to the developers of the universe, you should have chosen a better design decision. But what can we do? Maybe it was just floating point error.
See, Ahmad is saying picometer. Yeah, so yes. We were right. He's talking about the unit measurement. So absolutely, right. Once things get really small, you have to take into consideration new rules.
Yeah.
And that's what limits. It's the whole reason quantum computers exist. If on the quantum scale, computers work the exact same way, if physics on the quantum scale work the exact same way as on the classical scale with big things, we wouldn't need quantum computers. Yeah. We would just continuously to infinitely just make them smaller and smaller because there would be no underlying science for quantum.
It's almost like with regular computers, as we try to make them better and smaller, quantum computers in quantum sort of mechanics, inhibit us from doing that because we're trying to create classical computers here. But then you go over to the world of quantum and we're leveraging those abilities to do all kinds of like really weird things that we never thought were possible, which is why we require a completely different mindset. And I mean, we talked about how understanding, compilers helps you program better in languages, but understanding the underlying compute architecture can also help you in your algorithms. And I gotta say, if you're a developer working on classical technology, you've got to throw everything you know out the window before you start working with quantum, right? It's a whole different world of compute. And so like the algorithms that you thought you knew won't work in quantum. You need to relearn that new math, that new sort of quantum mechanics and how things interact. I think that's really important. It's like with a computer, you understand the idea of addition, for example. So when you do a for loop for I and 1 to 5, you're doing 1 plus 1, 2 plus 1, 3. You understand these things. Similarly, with quantum computers, you need to understand things like quantum superposition and entanglement and what that means, and how you collapse all these quantum bits into a single state, which is your answer. You have to understand what all these things mean, which I think is a whole different world of compute altogether. But it's still possible to learn. It's just completely different from regular computers.
Yeah, just one example before we end off. If you have like a byte of information, and so you have your ones and your zeros, just because you looked at the first one, let's just say the first bit. If you just look at the first bit and you say it's a 1, that doesn't tell you anything about the next 7 bits. Mm-hmm. All you know is the one you just looked at is a 1. But in chemistry and quantum physics and the quantum principles, we know things like Pauli's exclusion principle, which states if you look at an atom, there's no 2 electrons that can have the exact same, what we call quantum numbers of specific value, but there's no 2 electrons that can have the exact same set of numbers. We talk about their location and their spin and their magnetism and all these other kind of factors. So what that means is if I'm dealing with, let's just simplify it down to 2 bits, and I look at one of them and I say, okay, well, this first bit is a 1. I am actually able, using quantum, entanglement and all these other things, to create this entanglement that tells me if this bit is a 1, I know for a fact that the other bit is a 0, mm-hmm. and vice versa. You can create that sort of entanglement that says, because I know one, I know the other. Mm-hmm. And so if you were to imagine, throw away everything we know about quantum computers, and I said, I'm going to build an entire computer based on this principle alone, this idea that I can know one bit and therefore know the other bit, that immediately cuts the amount of bits I need to look at in half. for everything ever because I can immediately say, okay, well, the first bit is a 0, so the next bit is always going to be a 1 because of this entanglement property I've built into this hardware kind of thing. So that immediately all the bits I need to, everything gets split in half because I don't need to check the other half. I can just look at the first half and immediately know the second half. Mm-hmm. And so you take that, you throw in, the things like the state of quantum particles and how long they exist for, and all these other factors, and suddenly you get a very, very, very complex machine that doesn't work the way we already looked at. Just splitting the bits in half already changes, the way things work, and now you're throwing in all these other principles, and you have a machine that very different entirely, just completely different architecture from the ground up. And again, because it's based on these principles that allow us to change the way the classical computer was looking at it.
Mm-hmm. Absolutely.
That's my little spiel.
Completely reinventing compute.
Yeah, literally, we are reinventing compute. But that is all I have to say. These are all the questions I have for you, and for now, at least the audience has for you. So we're going to close off here, and I'm going to say thank you, first of all, to the audience for being such a great audience. As always, I'm always very lucky to be here and talk with all of you. You have some great questions. I spend all my time with this guy, and I never think of these kind of questions. You guys are probing his mind for me. Thank you very much. Some great. Thank you for letting us know about the network issues when we were having them. I have the stream open, but I sometimes pause it, so I don't always catch the network issues that are being had. So thank you for sticking through us with these network issues. And thank you, of course, to Tanmay for this Ask Tanmay special, letting us probe your mind over and over again for the 3rd or 4th time, I believe now. And hopefully we'll have more in the future where we get to go inside the mind of Tanmay.
Well, it's our 3rd, but I'm sure we'll be doing much more in the 4th as well. Really looking forward to that. And of course, thank you, Michael. I literally called you out of nowhere this morning, and I'm like, hey, we got 40 minutes. Do you want to do an Ask Tanmay special?
Literally woke me up, by the way.
Yeah. So this was really, really fun. And of course, again, as you said, huge thank you to the audience. Without all of you sending in these questions and sort of, giving us these sort of things, really interesting things to talk about, we wouldn't be able to share it. So thank you very much all for doing this. And of course, any questions we couldn't get to, feel free to leave them down in the comments or save up for the next Ask Tanmay special, because I'm sure that will